the sensor. Sensor is going to the material with that energy, interacting with the material, getting back the information of the material, coming to the equipment. Equipment will compare what I have given to the sensor, what I am getting back, what is the difference. That difference is coming from the material condition, and then it will analyze it, it will record it. Okay, so that is the, in any NDT process, this is the process. So in EDDY current testing, the sensor is test coil. Okay, so the test coil is on the basis of the winding. See, in the test coil, what is there? There is a copper winding. In that, the current is going through the copper winding. Then there will be magnetic flux around the copper winding, and it will interact with the material. So in that winding, on the basis of the winding, how you can do the winding, there are two types of. One is called absolute coil, another is called differential coil. Absolute coil is having only one winding, so it will measure complete change. Any changes there, absolute coil detect it. Differential coil, there is two oppositely winding. One winding is like this, another winding is like this. So it will compare nearby area. Okay. So for larger defect detection, for getting the material properties, absolute coil is used. For a smaller defect detection, differential coil is used. Okay. So this is the difference in absolute and differential. So absolute coil is sensitive to total change, differential coil is sensitive to localized change. Like any wobbling variation, probe movement variation, temperature variation, that is not in the differential coil, but it is all phenomena are there with the absolute coil. Next. So another type of is called two types, single coil and double coil, or driver pickup coil. Single coil is one coil will act as a transmitter as well as a receiver. In double coil, you have a transmitter, you have a receiver. So that receiver can you make any type. In the single coil, there is a fixed shape. Next. Then on the basis of probe geometry, there is surface probe, bobbin probe, encircling probe. Okay. So for flat product testing, like plate testing, you have to use the surface probe. If you want to measure the like electrical conductivity, magnetic permeability variation, like ferrite measurement, austenitic electricity weld, you have to use the surface probe. For the tubular product, there are two types of coil. One is called bobbin coil, another is called encircling coil. If you want to measure the outside of the tube, you have to use the encircling coil. If you want to measure inside, you have to use the bobbin coil. During manufacturing of the tube, mostly encircling coil is used. During in-service inspection, when the tube is in installed condition, you have to use the bobbin coil because OD is not accessible. Now the next step has come. As you have seen that eddy current decreases exponentially from the surface to inside. If you are using only encircling coil, it is more sensitive towards OD. If there is a 5% on the OD changes, it is equivalent to 20% in the ID change. If you are putting 5% depth on the OD and 5% depth on the ID and you are using encircling coil, it cannot give the same signal because it decreases exponentially from OD to ID. Okay. So if 5% on the OD because of more sensitivity, it is equivalent to 20% on the ID. Okay. Similar way, if you are using only ID, it is more sensitive to the ID. Okay. So if you want to get the complete, you don't want to miss anything, you have to use both. Next. So surface for plate and seat, surface probe is having lift off. Lift off is gap between the probe and the object. Okay. So even in our relationship, okay, relation is like a fire. You should not touch the fire and you should not get away from the fire. Then only you will get the heat. Okay. So like Like this in electromagnetics also, if you put the probe here and object is here, there is no interaction. Okay, so object and probe should keep nearby, but it should not touch. If it is touching, there is no electrical problem, mechanical problem will be there. Your probe will get rubbed on the surface due to friction. Okay, so there should be some as minimum as possible gap, and that gap is called lift off. Next, and wait. See this, there is a edge effect and end effect. On the because this is a coil, the magnetic flux is surrounding it. Okay, so in the plate, coil is here, magnetic flux is interact with from some distance because of edge. Okay, so this much area you cannot test, because from at a certain distance you are getting the signal of the edge. So in eddy current testing, if somebody is telling that I am totally testing everything, not possible. In the edge up to coil diameter you cannot test. Okay, so that is called the edge effect. Next, then in the bobbin or ID coil, there is fill factor. Fill factor means, again, it is a filling, like you are filling water in the bucket. If bucket volume is 10 liter, how much water you are filling? Like that, this is the tube, you are putting the probe inside. How much cross-sectional area you are filling with the probe? That ratio is called fill factor. Okay, so fill factor is basically ratio of the coil diameter to the tube diameter. In the case of encircling coil, the fill factor is tube diameter divided by coil diameter. But in case of bobbin coil, it is a coil diameter divided by tube diameter ka whole square, because it is a ratio of the cross sectional area. Okay, and that fill factor should be as maximum as possible. As maximum means you can put 100%, but again it will not move, it will be tight fit. Okay, so it may be 90%, 95%. So in surface probe you have seen lift off should be as minimum as possible, but fill factor should be as maximum as possible. Okay, and then there is a end effect, like edge effect in the plate testing. A certain edge you cannot test. Like that in tube also, if the coil is here, from there this edge is coming, end is coming. So in the case of tube testing, it is called end effect. Next. So encircling coil or feed through coil, same thing like bobbin coil. End effect, there is a fill factor. Next. Now variables affecting eddy current testing. What are the variables affecting eddy current testing? The first is electrical conductivity, second is magnetic permeability, geometry, edge effect and effect. Okay, so first two is material property, electrical conductivity and magnetic permeability. Higher electrical conductivity, more eddy current generation, more sensitivity. Higher magnetic permeability, again more eddy current generation, more sensitivity. Okay. But at the same time, when there is a higher eddy current generation, higher opposing force, less depth of penetration. Okay. Then geometry, like it is a flat geometry, circular geometry, some mobility is there. Okay. So it will affect the generation of eddy current. Then edge effect and end effect. Test coil variables are test frequency, fill factor, lift off. So basically in all eddy current phenomena you can see only variable which is in the hand of operator is frequency. On that basis you can play anything in the eddy current testing. If you are using higher frequency, your sensitivity will increase, but depth of penetration will reduce. Like if you are doing the material property, you have used the less frequency. You are doing the defect detection, again depending upon the sensitivity. You want to a small defect, you want to near to the surface, you have to a higher frequency. Like that, frequency is the only parameter in the head of operator by which he can play during eddy current testing. Next. So lift off is the effect, the interaction. It affects the sensitivity. Lift off should be as minimum as possible. Fill factor same in the case of tubular product. It should be as maximum as possible. It is a ratio cross sectional area. Then edge effect, in case of plate it is on one coil diameter around. In case of tube it is an end effect. Again one coil diameter from the end cannot be tested. Next. So how do you design the coil? During the design of the coil, what should be considered? All these variables should be taken care during the design of the coil, like geometry of the test object. Coil should be designed in such a way that it should be nearer to the test object. Okay. Then material of the test object. How material will affect the coil design? Because material is having different material property. On that basis, you have to select the frequency for given standard of penetration, and for that frequency you have to design the coil. Okay. So any matching surface, if same characteristic material is matching to each other, then there will be maximum power transfer. So coil is connected to the equipment, okay, and at what frequency you are setting in the equipment, same frequency should come to the coil. Then this flow characteristics, again you want to a smaller flow detection, larger flow detection, accordingly coil geometry will change. Fill factor, if sometimes the situation demands like that, you have to use less fill factor. Like there is a bend in the tube. If you use 90%, 95% fill factor, it will not go. But if you use 70% fill factor, it will go to the bend. You are testing at the compromise of the sensitivity. So then frequency is ultimate for which this coil should be designed. So a coil is used only for a particular object geometry and particular frequency. So if you are designing a coil, say 100 kilohertz, 30% more, 30% less, it can work, but it cannot work very less frequency, it can work for high frequency. Next. So reference standard, basically to set the sensitivity of the equipment, reference standard is extremely important. Okay. So reference is basically comparison. See, in real life you should not compare with others, because it always leads to jealousies. Okay. But if you want to decide something, you have to compare it. Okay. And that comparison should be in such a way you compare only two same thing. You cannot compare apple with the orange. Like everybody is telling that he has passed from the same class, he should perform same, but it cannot be, because the processor fit in the two system is different. Okay. So for any eddy current testing, you need a reference standard to set the sensitivity in the equipment, and that reference standard should be made of the same material, same chemical composition, same heat treatment, same manufacturing process. Okay. So that whatever you are comparing, it is one to one. Next. Then the test parameter selections, frequency, phase, gain. These are the three variables. Nowadays, many other variables have come into the picture, but basic fundamental is these three. So frequency, it is a compromise between the SDP and the sensitivity. Phase is generally set in the probe portion in wobbling in the horizontal direction. okay, or the gain you have to get the appreciable signal. Gain should be such that, okay. Next, then the types of ECT, different types of say impedance testing, phase analysis testing and modulation analysis testing. If you are measuring the complete impedance change, like you want to measure the electrical conductivity measurement, it is impedance testing. Single coil is used, okay, complete impedance variation. Then there is a phase analysis testing where you are measuring the phase angle. On that basis of the phase angle you are giving the decision, okay. So in the phase analysis testing there is a vector point method, then linear time based, ellipse method. Linear time based and ellipse method is not used nowadays, it is earlier technique. Now vector point method is used, in which you are getting the signal by connecting all the vector points, variation of the magnetic flux linkage with the material, and then you are getting the phase. Depending upon the phase you can say up to what at what depth this defect is there. And then the modulation analysis is basically based on the frequency analysis. All this impedance phase analysis is based on the impedance, but modulation analysis is based on the frequency. Generally in eddy current testing the speed does not matter, but in modulation analysis speed matters, because frequency changes as you more movement changes, okay. So like wire testing, this modulation analysis is extremely important. Crane hook wire. Next. So in the eddy current equipment, as you saw, there is a power source, oscillator. Oscillator controls the frequency. See, in the line you are getting 50 Hertz, that is connected to the equipment, but if you want to test the material you have to use 100 kilohertz, 200 kilohertz, 500 kilohertz, okay. So how this 50 Hertz is getting converted into 100 kilohertz, that is done by the oscillator, okay. And again 220 volt you are getting from the line, and whatever testing is done, that is done on 10 volt. So there should be a step down transformer inside the machine that will convert 220 to 10 volt, okay. Anywhere you are operating with hand, this open circuit voltage is 25 volt. It should be less than that, otherwise shock will be there. So oscillator gives a frequency of desired frequency signal to the test coil. Test coil is object with the test object, interact with the test object, then that changes may be very small, that should be amplified, so it should go to the amplifier. Then phase detector will differentiate what is given to the coil and what is the now, and that should be the quadrature sample. It is converted to X and Y. That Z is combination of R and XL, so R in X, XL in Y. And then on the CRT screen you are seeing the signal, and it is recorded on the strip chart recorder. Nowadays it is just on the screen also. Next. So this is the ECT equipment. It has a different connector, power source connected to the equipment, then coil is connected to the equipment, coil is interacting with the object, and you are getting in the signal on the screen. Next. So these are the different ECT signal, like 3 signals are shown in this. This is the absolute, these are the differential, okay. So in absolute, single coil is there, so you are getting only one sided loop. In the differential there are 2 coil oppositely winding, so you are getting opposite signal, 8 shape loop, okay. So in this case, during eddy current testing, if you set the probe wobbling motion in the horizontal direction by setting the phase, you will get the signal from the through-wall hole is at 40 degree. So that is the reference line. If you are doing testing from ID side and you are getting the through-wall hole at 40 to 45 degree, then whatever signal is coming from the 0 to 40 to 45, that is from the defect is originated from the ID side. If you are doing the testing through ID side, through-wall hole is up to 40, so 0 to 40 any defect is coming is from the ID side. Okay, and if it is more than 40, then that defect originated from the OD side. Okay, and depend upon the different angle, the different phase depth and the different depth of the defect is there. Okay, so there is a ID signal, pole signal, OD signal. In absolute coil only one side, in differential coil there are two signals. Next, then application of eddy current testing. Basically, eddy current testing is used for surface and subsurface flow detection. Why it is only for surface and subsurface flow detection? Because eddy current decreases exponentially. Okay, but when the tube wall thickness is very less, 0.5 mm wall thickness, 1 mm wall thickness, in that case it can be taken as a volumetric. Okay. In critical composition component, even though 1 mm wall thickness, 0.5 wall thickness is there, eddy current is a volumetric examination, still you are using one more complementary examination, that is ultrasonic testing. Okay. So anything is missed by ultrasonic can be detected by eddy current, anything missed by eddy current can be detected by the ultrasonic. So if you do not want to miss anything, the two techniques are used, but at the cost. So first application of ECT is flaw detection. It may be gradual thinning, absolute coil, like in carbon steel tube there is a uniform corrosion, so you have to use the absolute coil. In the austenitic stainless steel there is a localized corrosion like intergranular corrosion, stress corrosion cracking, intergranular stress corrosion cracking, pitting corrosion, crevice corrosion. So for that differential coil is used. Then the conductivity measurement, if you in the soft load many components gets mixed. How do you differentiate? All are look alike, and like aluminum, pure aluminum and aluminum magnesium alloy, same. But how do you differentiate it? By measuring the electrical conductivity. Then coating thickness measurement, like paint thickness, metal to metal, and then ferromagnetic material, conductive material combination. So if there is a non-conductive metal over the conductivity is coating, if there is a conductive over the conductivity is a plating. Okay. So coating thickness is based on the lift-off measurement, because non-conductive material it only increases gap, air gap. So it is on the lift-off, and for the conductive to conductive like nickel plating, chrome plating on the stainless steel, you have to use the electrical conductivity difference, and that is based on the thickness measurement. And then the residual stress measurement, because residual stress impaired the movement of the flow of electron, it will change the electrical conductivity, and that way you can measure the residual stress. Like cold work condition, you will get lots of noise in the cold work material. Then in the metal sorting, it is again based on the electrical conductivity. Next. So heat exchanger tube testing is one of the major umpire application of the eddy current testing. Okay. Still in the market, no other technique, only eddy current testing is there for heat exchanger tube testing. Okay. Ultrasonic testing, iris is came into picture, but it is too slow. If you want to characterize a small area, you can use iris, but full-fledged testing, eddy current testing is only used. Okay. So during installed heat exchanger tube, you have to use the bobbin probe. Okay. Bobbin probe of desired frequency. Based on the tube wall thickness, you are calculating the frequency. Okay. On that frequency is used as test frequency. Then in the heat exchanger, there is a support plate. The first is tube to tube seat. Then there is a tube, long tube is there, 5 meter, 10 meter tube is there. So in between there is a support plate is there. Okay. It guides the flow of the fluid as well as support the tube. So due to vibration, tube to support plate, there is a thinning in the tube. Okay. So in the different location inside the tube, there are different corrosion. Like tube to tube seat, in the tube seat there is a crevice corrosion. Tube to support plate, there is a fretting. Inside the tube there is a pitting, there is a stress corrosion cracking. If it is a U-bend tube, there is a flow assisted corrosion. Then this cavitation. So either due to mechanical interaction or due to corrosion interaction, the tubes get degraded during the service, and that degradation needs to be monitored. Okay. So bobbin coil is used, and then this bobbin coil, the two most difficult location to analyze the eddy current signal in this. One is tube to tube seat location, another is tube to support plate location. So if you are using single frequency, you will get at the support location the signal from the tube as well as from the support plate. Okay, but you want to test the tube, not the support plate. So you have to use the two frequency. One frequency is sensitive to the tube, another frequency is sensitive to the support plate. So like 100 kilohertz you have calculated the frequency, you have to use the another frequency which is half of the test frequency, prime frequency, or 1/4. So 100 kilohertz is test frequency, so you have to use the 50 kilohertz in the second channel, and then the signal from the two channel is mixed together. Okay. So in the prime frequency you are getting the more sensitive towards tube. In the second frequency, secondary frequency, subtractor frequency, you are getting the more from the support plate. And actually nowadays you are just touch the button, mixing, your signal gets nullified due to support plate. But earlier what happened, this support plate signal you are getting that on the both the channel. Now what you are doing, the second support plate channel, you are adjusting the phase and gain. You are adjusting the gain in such a way that this signal from the second channel should become equal to the first channel, and you are adjusting the angle in such a way that the second channel is 180 degree apart to the first channel, so that equal and opposite signal will cancel the support plate signal. Then in the prime channel or in the max channel you are getting only tube signal. Okay. So that way this multi-frequency eddy current testing comes into picture, in which two frequency is used, and after getting the nullification of the tube support signal, you are getting the signal from the tube only. Next. So prime frequency signal, subtraction frequency signal, these two signals are coming into the mixed channel, and then it is giving the signal from the tube only. Next. But in all the case you can see you are making two signal equal, but that two signal is coming from the different frequency source. So if their source are different, you never make equal. You make it similar, but it cannot be equal. Okay. So always in mixing channel you can see some small differences. So a small signal will always come. Okay. So this is the one more application is coaxial tube. The two tubes are, then at the interface if there is a gap you can get signal. If there is no gap, you will not get the signal. That you can characterize it. Next. So if there is a gap on the interface, you will get the signal corresponding to the different gap depth. Next. So advantage and limitation of eddy current testing is, advantage is it is non-contact testing. Then online or offline data analysis, you can give the immediate result or you can give the offline result. It is post-processing data is not necessary. Online you can tell the whether it is acceptable or reject. Very fast, repeatable and reliable. Automation is possible. So fast is the main advantage. Without touching the material, you can do the testing, and in one day you can test thousands of tubes. Limitations is only for conducting material, then separate coil for separate object, only for surface and subsurface flow. The costly equipment is used, and then a skilled operator required for data analysis. Because in any other technique you can say lots of persons are available, but in EDDY testing very few people are available because of this complexity of the signal. Next. Different advanced entity testing is whatever limitation is there for the conventional testing, new techniques has coming. Like in ferromagnetic material there is a problem during the normal conventional EDDY testing. There is magnetic bias technique, then remote field EDDY testing, alternating current field measurement testing is there. Volumetric flow detection, there is a pulse EDDY testing is there where the depth of penetration can be attained more. And then the testing for non-conductive dielectric material, there is a microwave energy technique. Next. So codes and guides. So there is always a regulation. Wherever there is a human body, it needs a regulation. Otherwise, if there is no constitution in the India, it will create a lots of havoc. So you have to always do the things as per regulation. Okay, so different codes and standards are there in EDDY testing. So different IS code, ASTM standard, then ASME codes are there to guide the how to do EDDY testing, what to accept, what to not to accept. So that guidelines is given in the. Okay. Thank you.
Check. If you have any questions, one or two questions.
So this technique is only for native material like original manufacturer like pipe plates or welding also.
Yes. In the codes and the standards, EDDY testing is not there for welding. Welding for welding there is for welding there is a surface defect, volumetric defect. For surface defect detection, LPT is there, MPT is there. For ferromagnetic, MPT. For general, it is LPT. And for volumetric defect detection, ultrasonic and radiography. But please keep in mind, if there is a in-service inspection during service, it needs to be inspected, then use the same technique. The problem is during manufacturing, people are using radiography, and during in-service inspection, radiography cannot be used, so ultrasonic testing. So that gap area should be always addressed. As far as EDDY testing is concerned, it is not given in the code, but you can very well do EDDY testing in the weld also. Even yesterday I saw after weld flushing, no technique can give where is the weld. But if you do the EDDY testing, it can be clearly differentiate. There is a weld, there is a baseline, there is a HH.
Okay, sir, there is a limitation for AC current only.
Okay.
It is not for DC limitation. This is limitation.
By DC you cannot generate EDDY test.
Yes, sir. But in some urban areas there is work is in progress, but we have to apply the EDDY current process. Then we cannot apply it.
Which area?
Urban area, like in cross and pap.
The EDDY test is frequently used anywhere.
But
there is no
AC power is not available over there.
AC power is not available there.
Yes,
then you have to transform that DC to AC. Now inverter converter is there, no? You can transform it.
Sir, data is recordable on digital basis.
Yes.
Thank you, sir.
Hello, sir.
Yes.
In coaxial tubes, only we detect gaps or any defect also?
Defect also depends on the what, see, the parameter, test parameter is decided based on the what you want. Okay. In coaxial tube, if you want to test the inside the tube, defect inside the tube, you have to use very high frequency so that it will not go deep inside. If you want to test the outside tube, you have to use the very less frequency, so you can test the outside tube, not inside. So depending upon the requirement, you have to select the test parameters.
Okay. Thank you, sir.
Sir, which defect we can see in the eddy current? For example, straight tube or U-bend tube? Means lamination, means crack,
See,
we can see in the eddy current?
just I will tell you. See, ED current is a circular current. You can detect a person in the society who will create a disturbance for you. Okay. Like in this class, 3 persons ask the question. Okay. So I will remember these 3 persons. Hana? The rest of the person is not so much identifiable as these 3. So in eddy current also, whatever defect is there, if it will disturb the path of the eddy current, it can be very well detected. So any defect parallel to the eddy current, it cannot be detected. If it is perpendicular to the eddy current, most sensitive, even it is in angle, it can be detected. So only parallel defect cannot be detected.
Sir, only one more doubt.
Yes.
Sir, as you have seen in screen, we cannot examine the complete surface.
Yes.
Then we have to apply the another method also to balance surface to examine.
I have not given the solution to that.
Yes.
Even by eddy current testing, that complete, you cannot do complete, but you can go to the nearby. How it can be done? If somebody is very hungry, you have to give food to them. Right? So magnetic flux is going like this, you have to put silt, so that the flux is not coming like this. If you put silt here, it will restrict here. Okay. But any process, if you are restricting, you have to pay for that. Okay. So at the cost of sensitivity. Okay. If you are sealing using the conducting material, it will again create the eddy current. It will oppose the magnetic flux to the coil. So your sensitivity will be reduced. Okay. But if you are using the ferromagnetic material, your sensitivity will increase, but your depth of penetration will reduce. Okay. So every technique is having its own limitation, and nowadays world is growing to overcome that limitations. Okay, so by magnetic sealing or conductive sealing, you can go to near to the edge. Again, it cannot completely to the edge. That limitation is with any techniques. Okay, because in any NDT techniques, you are passing some source of energy, and it cannot go a straight line. Wherever energy will move, it will spread from the source.
Okay, thank you, sir.
So, thank you very much, sir, for giving enlightenment. Very good. So, he is there until evening, so you can always ask questions also during lunch time and all. So, not a problem. But now it is time to felicitate him. So, I thank from ISNT Pune chapter that you have come here. So, to continue with the topic what Arvind Kumar has delivered, I request Arjun V. He is from IGCAR. He has received his MTech degree. basically Department of Atomic Energy, Homi Bhabha National Institute, Kalpakam, Tamil Nadu. He has been a scientific officer at IGCAR on the development of electromagnetic sensors for his research interests include finite element modeling in electromagnetic ND, sensor development, and signal image processing. So over to you, sir. For
Can I use the column mic? Or- Am I audible? Yeah. Huh? Oh, okay, fine. Yeah. So, good morning, everybody. Am I audible? So, I'm Arjun. I'm coming from Indira Gandhi Center for Atomic Research. So, I will just, as continuation of lecture given by Arvind I will just take away from there. So, so now that you have gotten feel of eddy current testing, we will see in depth how the eddy currents are getting distributed in various test geometries. So our common test geometries are, they can be planar surface, they can be circular geometries, and they. Acha. No, I may one thing say. Yeah, yeah. Yes. So, right. So the all these test geometry of the test specimen or the material properties, all these things will affect the distribution of eddy currents in the specimen. So, and another major parameter that affect the distribution of eddy current is test frequency. So you have all seen what happens when frequency increases, what happens to the penetration? Can anybody recall? What happens with the depth of penetration when frequency we are increasing? It reduces due to skin effect because it is inversely proportional to test frequency. Next slide. So coming to a plate geometry, usually for plate geometry we use a surface probe. Like if this is a plate, we use a surface probe, and the probe will have a coil whose winding is parallel to the plate. Okay, so the induction also happens parallel to the plate. So, but only thing is that the direction of current flow is opposite to the direction of the excitation current. That is due to which law? Lenz's law, right? So because it has to oppose the course. In a planar geometry, the direction of induced current will be always parallel to the surface. The eddy currents will always form a closed loop and it attenuates with the depth. So here, now you want to detect a defect using this current. So what type of a defect can give more sensitivity? Suppose a defect is oriented parallel to the direction of current flow, and another second case a defect is oriented perpendicular to the direction of current flow. What do you think? Which will give more response? perpendicular. Why? Huh? When it is parallel, the disturbance to the flow of eddy current is minimal. But when it is perpendicular to the current flow, it will have maximum disturbance. So more disturbance, more perturbation to the field, so more change in impedance. So we are finally seeing, we are not measuring the eddy current per se, but we are seeing an indirect effect on the impedance change in the coil. Next. So again, factors of, I have already, last speaker has already mentioned it. So one of the major, some of the major factors are dimensional property. We call it as end effect or edge effect. So then the electromagnetic, the properties of material, which will influence the skin effect, and basically discontinuities, which are flaws or defects that we are trying to detect. Next. So coming to end effect. So for plate, we call it as end effect. For tubes, we call it as edge effect. So, for plates, we call it as edge effect, and for tubes, we call it as end effect. So we will see how it is happening. So in the first case, probe is, in all the three figures, the induced eddy current is thematically shown, okay? So in the first case, probe is slightly far away from the edge of the plate. So eddy currents are not disturbed by the edge. But when we are moving probe closer to the edge, what is happening? The eddy currents will start seeing the edge. So edge is like a big discontinuity. So due to that discontinuity, there is a large change in probe impedance. So due to that, what happens? When such a large change is there, if there is a defect that we have to detect near this edge, that will get masked by this large change in impedance. Okay, so this is a problem in ECT. So we call this, these edges will be a dead zone, basically, for ECT, right? Similarly for tubes. So suppose this is a tube I'm planning to inspect, or a road I'm using an encircling probe and I'm bringing it near to the edge. So here the edge will be seen as a big discontinuity. In the tube we call it as end. So here you will get a large impedance change. So this impedance change will mask the small defect change. So this is so up to a particular length from the edge is a dead zone, right? So there are various ways to overcome it. We can restrict the propagation of the field, or we can restrict the flow of eddy currents by various ways. And this can be used as an advantage. This eddy current testing is not only used for defect detection. So we can use eddy current testing for proximity sensor, as a proximity sensor. So proximity sensor is nothing but you are just seeing how near the object is. So this edge effect or end effect can be used in that way as well. Next slide. So this is already familiar. So that is that right side, that picture, it depicts how the eddy current is distributed across the cross section. So maximum eddy current is induced near the surface, and as we go across the thickness of the specimen, the the density, current density, it exponentially decays. And Sarah has already explained what is the significance of standard depth of penetration, right? So it is given by this formula, and this we use left and right. This is our formula, the formula that we use in ECT. So from this formula we can understand that depth of penetration is inversely proportional to test frequency, magnetic permeability, and electrical conductivity. Suppose you want to inspect a specimen and you want to focus on the surface. So once the specimen is fixed, its magnetic permeability and material properties are fixed. So then we can play with the test frequency and adjust the data. Suppose you want to test on the surface, you go for a higher frequency or lower frequency. Surface. We only want to inspect the surface. Higher frequency. Because higher the frequency, lower the delta. So lower the penetration. So almost all eddy currents will be focused on the surface of the specimen. So it will be more sensitive to surface defects. Similarly, suppose if you want to inspect a ferromagnetic material, so it will have large magnetic permeability, right? So in that case, which frequency you would go, higher frequency or low frequency? Ferromagnetic specimen means permeability mu value will be higher. Basically, mu r will be of the order of more than 1000. So you will go for a higher frequency or a lower frequency? Lower frequency. Because already mu is high, so you have to reduce the frequency so that delta is, penetration is there. Yes. Now, a defect is there, you have the probe. You are keeping on top of the defect. It doesn't ensure that defect will get detected. If you see the probe properly, carefully, the probe coil is fully present on, probe will be usually wound on some non-conducting material, we call it as bobbin, right? And so in the center there will not be any coil. Coil is present on the outer side of the bobbin. So that cross section is shown there as the coil. So maximum eddy current will be induced wherever coil is there, because coil is to coil only current is flowing. So wherever current is there, there is magnetic field. So that magnetic field will couple with the test object and maximum eddy current will start from there. So if you see, wherever that coil is there, there only you will get maximum induction. So induction at the center of the probe will be, in such probes will be minimum. So just by keeping the probe on top of a non-defect, it doesn't ensure that defect is detected. So for that, what you have to do? You have to move, right? So that the defect is, passed across the sensitive area of the region of the probe. So if you consider that minimum sensitivity is at the center, and as you move away from the center of the probe, sensitivity of the probe increases, and it will be maximum at the center of the coil. By center of coil I mean wherever the winding is there, where induction is maximum. Okay. So for suppose such a coil, if I am moving across a defect, suppose this is a test object with a defect, and I am moving a coil. So I am just schematically showing the probe like this. So this is one part of the coil and this is the other part of the coil, and I am moving it across like this. So how your signal will be, you will first this part will see the signal, see the defect. So you will get one peak like this, and it will become maximum when this is just under the defect. And then it will become, when the probe is at the center, it will become minimum, and when the other side passes, you will get the induction. Again, it is happening in the opposite direction because field is in the opposite direction. So a typical signal will look like this. Next. So liftoff concept is already explained, I think. So liftoff represents the gap between the test specimen and the probe. So basically it determines coupling, electromagnetic coupling with the sensor and the test specimen. So we should always ensure minimum liftoff for any testing. Whether we can keep a liftoff 0, minimum liftoff is always good. But what happens if I keep liftoff 0? I told that when we are doing testing, you should not keep the probe in one location. You have to keep moving the probe, right? So what will happen? Liftoff 0 means I'm touching the test specimen, right? And if I keep moving, what will happen? The probe will get physically damaged after some time. So always some gap should be maintained, but that gap should be minimum as possible. Now, we can quantify it like this. Suppose you take, so the figure has shown one probe with a particular diameter D, and it is trying to find out how the induced voltage in the coil due to the defect, defect which is it's a surface effect, how it changes when liftoff is varied, right? And when the probe diameter is changed. So we will take some 4 cases. So they have shown when for diameter 5 mm, 7 mm, 10 mm and 25 mm. So the maximum amplitude will come when the liftoff is 0. So it is normalized to 1. The maximum amplitude for all the cases is normalized to 1. And when liftoff increases, obviously the amplitude will drop. Now you see that drop, the rate of drop. For a smaller dia probe, for example 5 mm dia probe, the rate is so fast. With a small change in liftoff, suddenly the defect amplitude is getting dropped. But that rate of drop is minimal compared to the smaller dia probe, it is minimal for 25 mm. So suppose you are going to do a testing and you cannot keep a liftoff probe very close to the specimen. So in such cases, you should go for a bigger dia probe or a smaller dia probe. From this, what do you understand? Bigger dia. Because bigger dia will have minimal influence to change in liftoff compared to smaller dia probe. Everybody got it, right? So this doesn't mean that we can keep on increasing the dia. So liftoff is a problem, so I made a very big dia probe, that also will not work. We will see what happens. So if you take a particular probe and you find out how the induced voltage in the probe is varying with respect to the length of the defect. Suppose the 100% it is shown for a defect whose length is much greater than the probe dia. For a theoretical calculation, we will consider it as an infinitely long defect. Okay, so its amplitude is taken as 100%. And for a particular dia probe, for example, here 2 probes are shown. One is 7 mm dia probe and another one is 1.3 mm dia probe. So when you take 7 mm and when the length of the defect is reducing, after a particular point, the defect amplitude also will start reducing. Can anybody tell why defect amplitude is, signal amplitude is reducing when defect length is reducing? So impedance has 2 parameters, probe impedance has 2 parameters, one is amplitude and one is phase angle, right? So amplitude is proportional to volume of the flow and phase angle is proportional to depth of the flow. So here depth is maintained constant, here we are looking at the amplitude. So when length is reduced, proportionally volume of the defect reduces, so signal amplitude also drops. So we can see that drop in amplitude is almost, for 7 mm dia, it has dropped to almost 70% of maximum amplitude when defect dimension is almost equal to probe dimension. So for a 7 mm defect, the drop in amplitude is almost 70%. But consider what happened for the small dia probe. It has almost dropped to near to 30% when the defect amplitude, defect length became equal to the probe dimension. So from here the takeaway is that when you select a probe for a particular examination, the minimum dia of the probe, the dia of the probe should be at least the length of the minimum defect that you are trying to detect. It should not be greater than that. If it is bigger than that, the sensitivity will be much lower. Okay. Once again I will tell. If you are doing an insection, the diameter of the probe should be at least the the length of the minimum size of the defect that you are trying to detect. If it is bigger than that, that small defect may get missed out. Okay. Next. So here comes the effective diameter of the probe. So when I say a 7 mm dia probe or a 25 mm dia probe, doesn't mean that the probe will start seeing the defect only when the defect is at the edge. It will start seeing the defect much before. Why it is happening? Anybody can tell? why this probe will start seeing much before the defect approaches the probe. Exactly. So the diffusion, the eddy current diffusion is happening in all the three directions. Don't accept that it is only happening in the thickness direction. It is happening in X, Y, Z all directions, right? And it is following the same standard of penetration rule, right? So the effective diameter of a probe can be expressed as DCC probe physical diameter plus 4 delta. Up to 4 delta it can sense. But sensitivity, if you talk about sensitivity, it can, detection will start, proper detection will start after 3 delta. But it will start seeing the things from 4 delta onwards. But at high frequencies, what happens, this delta will shrink to a very small value compared to DC. So at high frequencies, the effective diameter will be almost equal to probe diameter. But for low frequencies, this effect will be more prominent. Now, before coming to this, I just want to introduce one. So we are talking about our sensor in eddy current testing is coil, basically an inductor, right? So, and we are measuring the impedance of the inductor. So impedance is a complex number, right? So we impedance is we use this letter Z for impedance, and the impedance has a real part and an imaginary part. So real part is resistance, DC resistance, and imaginary part is the inductive reactance XL. So XL is L omega. L is the self-inductance of the coil, and omega is the test frequency, means circular frequency, 2 pi f. So this suppose, and all our measurements in ECT we make in this impedance plane. Impedance plane where the x-axis is the resistance, which is the real part, and the imaginary axis, y-axis is the inductive reactance, XL. Okay. Now, here we do something called a normalization. So the normalization is done in order to make the testing independent of probe parameters. So I will tell how normalization is done. You take the impedance of the coil in air. So Z air, assume that Z air is R naught plus J X naught. So R naught is the DC resistance of coil, and X naught is the reactance of the coil in air. So specimen is nowhere nearby, only air is there, so there is no induced eddy currents anywhere. Now if I am bringing it near to a specimen, Z has become R plus Jx, suppose. Now I am going to normalize. So normalization is done like this. So I subtract the DC resistance part and I divide it with the reactant of the air. So this has become my real part now. And the imaginary part is the reactance I am dividing with air reactance. Okay, so now this is a normalized impedance, Z prime. So when I talk, now onwards when I talk about normalized impedance plane, so this impedance plane will be, the real part will be now R minus R naught by X naught, and reactance part will be X by X naught. So in a normalized impedance plane, can anybody tell what will be the value of impedance in air? R minus R naught will get, real part will be? R will become R naught, right? So the real part will get cancelled off. Real part is 0. What about imaginary part? X will become x naught. So imaginary part is 1. So 1j. So normalized impedance plot always the air impedance will be 1. So that is why, so it is now independent of the probe. Whatever probe you take, once it is normalized, air impedance is 1j. From there, now you can, so now from there only the impedance changes only due to specimen parameters or other test parameters, right? So we have made it independent. Now, this 1j I am just representing it here. And if I increase the test frequency, the locus of the impedance means how the impedance varies. It varies something like this. Suppose this is the 1j part, 1j point. It will vary in a circular, it varies like a curve. Okay. So that is how this curve is coming. So this is a normalized impedance planes are coming. This much you can follow, right? So in normalized impedance plane, the impedance will follow the locus of a semicircle. Okay. Now from there we'll start. Let me introduce another parameter called characteristic parameter. Okay. So this characteristic parameter comes from so this the governing equation of eddy current testing. If you think about it, it is coming from the Maxwell's equation. So you use the Maxwell's equation, and the governing equation will be coming in the form of a diffusion equation. Okay. And this diffusion equation, if you try to solve it analytically, they use some Bessel functions and they solve it. So there one parameter will come. So it is identical to something called wave number. So K it's called. So that parameter is called as characteristic parameter. I will tell how this parameter helps us in testing. So this now you take this characteristic parameter PC as r square omega mu r sigma, where r is mean radius of the coil, mean radius. So OD plus ID by 2 basically. Omega is the test frequency, 2 pi f. Mu r is the relative permeability and sigma is the electrical conductivity. Now I was talking about this normalized impedance plane, right? So this PC is a dimensionless value, by the way. And for any, suppose if you change the probe dimension, R will change. If you change the test frequency, omega will change. If you change the specimen, sigma will change. So all these things will affect PC. So for a particular probe, if you change the frequency, you always see that at this point, we call it as knee point, okay, where resistance becomes maximum and it is reduced. So at that point, this PC value will be always 10. Characteristic parameter will be 10. So that is what is shown there at different liftoffs. As liftoff is increasing, what happens? This curve becomes smaller and smaller. Okay. So at different liftoffs, at the knee point, if you see what is the value of PC, that PC will be always 10. Okay. Now why knee point is important is because the knee point is the place where you will have maximum discrimination between undecided variables and desired variables, decide our conductivity change. So undecided variable like geometrical changes or liftoffs, variations, and maximum phase angle difference means you will get almost 90-degree phase angle separation between these. So that is what we want. So we always try to operate, whenever we are doing testing, we always try to operate near the knee frequency where sensitivity is maximum, where discrimination is maximum. So when you, in this problem, we assume that the thickness is infinite. Okay, the delta is not playing an effect. Thickness is much bigger than delta. If when thickness comes into play, again everything changes. So if S frequency is high enough, and eddy currents are not theoretically anyway, it will reach the other end, but practically we are not getting any influence from the thickness, then we can use this parameter to always optimize the what should be the die of the coil, what should be the test frequency for getting the maximum sensitivity for the testing. Understood? Any doubt is there in this? I think this is bit. Only thing is that, once again I will tell, suppose you want to inspect a plate. So you have a very thick plate, assume that thickness is very large. You have to select the probe, you have to set the frequency, right? So you select the probe and frequency such that PC is 10, right? So when probe is selected, its dia gets fixed. So R bar gets fixed. So for that probe, what should be a test frequency so that it is coming near the knee region, so that you are getting maximum discrimination. Understood? Now, so they have simplified the formula. So this PC for a plate, you can straight away use this formula where if you rho usually, so conductivity of a test specimen we usually express in terms of micron centimeter resistivity. So in that case, you can use this formula straight away and you can find what should be the radius or what should be the test frequency. Okay, next. Now, if you want eddy current testing, if you want, yeah. Okay, it is, just go to the previous. The PC, that formula is there, it is the same formula, but instead of sigma, it is expressed in terms of rho, resistivity in micron centimeter, and it is for a non-magnetic specimen, so mu become 1, and mu naught value is already, that 4 by 10 to the power minus 7 is already plugged in. Then you can straight away use the formula. Go to the next one. So next one. You can straight away use this formula. R bar is again the mean radius of the coil. OD plus ID by 2. It is R bar square only. It is R bar square. Okay. Next. Okay. Now, if you want to use eddy current testing to measure conductivity or resistivity of material, we should always ensure that thickness is not affecting the impedance. If thickness is affecting the impedance, what will happen? Even though resistance or resistivity or conductivity is changing, the bigger influence will be from the thickness because it's a big discontinuity. So you should select a frequency, high enough frequency, so that delta is as small as possible. So here we will, we can use this condition. T should be at least 3 times delta. Ideally, T should be greater than 3 delta. So if you use that equation, whether you can see it, test frequency will come out to this formula, 22,500 by T square into rho. So rho will be in micron centimeter. If T is in mm, you will get test frequency in hertz. So this formula you can straight away use for conductivity or resistivity measurement, so that thickness is not influencing the measurement. Same thing, ECT can be used for thickness measurement also. Right? So in such cases, our disturbing variable mostly will be lift-off variations. So we want our lift-off variation to be what would I say? Lift-off variation should appear in a altogether different phase angle from the thickness variation. So that maximum phase angle is 90 degree. So we call it as F90, frequency at which this lift-off variation and thickness variation is almost 90 degree. So that will happen approximately when this condition is satisfied. This T thickness upon T by delta is approximately 0.8. So when you use that, you will get this equation. F is 1.6 rho by T square. Okay, so if you want to use ECT for thickness measurement, you have to use this formula. So again, rho is in micron centimeter, T is in mm, you will get F in kilohertz. I know it is a bit much, but once you start using it, you will get familiar. Next. Now, coming to tube. So till now we were talking about planar geometry. So in planar geometry, I introduced you to one characteristic parameter, right? So here also in tube circular geometry also, we have one parameter A. So this A is again coming from that solving of that diffusion equation for this geometry. So A will come out something like this. It is proportional to frequency mu r, and this D is, by the way, D is the die of the specimen, okay? And inversely proportional to resistivity. And there is one proportionality constant is also coming. Now, there I was telling that PC should be 10, right? So here we make this characteristic parameter, we will set it to 1 for tubular geometry. So the frequency at which A becomes 1, we call it as limit frequency. I will tell you how this limit frequency helps in tube testing. But just understand that this, we find out this limit frequency, this is the frequency at which A becomes 1, right? Bhaiya, next. Now, when you talk about circular geometry, we can have rods, we can have thick-walled tubes, we can have thin-walled tubes. So the limit frequency Fg for all the three geometries will be coming something like this. For rod, the diameter, that factor will be OD square, or basically dia square. And for a thick-walled tube, it will be thick-walled tube if we are inspecting from ID, using a bobbin probe if you are inspecting, then the diameter part will become tube ID square. And for thin-walled tube, if you are inspecting either by encircling or bobbin, it will, that diameter part will become D into T, Di into T, where Di is the inner diameter and T is the thickness. Okay. So this is how we get the limit frequency for three different geometries. Now we will see how to utilize this limit frequency for optimizing the test. Next. So this is again the normalized impedance plane for all three geometries. So the outermost one is for the thin walled, the middle one is for solid cylinder, and the innermost one is for a thick walled tube. So again here the funda is same. We have to operate at knee region, right, where you will have maximum discrimination. So that happens for a thick walled tube or for a rod. That happens when F by Fg, F is the test frequency, Fg is the limit frequency, then F by Fg ratio becomes 6. So, and for thick walled tubes, it happens when F by Fg is 4. For thin walled tubes, it is same as that of limit frequency. So, for a geometry, first find out what is the type of geometry, find the limit frequency, and then pick the ratio, and then that will be your test frequency. So this will ensure that you are operating at the knee region where you have maximum discrimination between lift of variation, undecided variables, and defect signals. Is it clear? Any doubt is there in this? I think, madam, you have doubt. No? Next. Now, if you want, suppose some tube testing you will have disturbing a lot of some ferromagnetic deposits or inclusions will be there. So that will induce as a noise to the defect signal. So if you want to have a good discrimination between noise from the ferromagnetic part to the defect, you choose the frequency such that F by Fg is 2. Okay. But if you want to have a good discrimination between surface defects and fill factor is basically change in fill factor happens due to wobbling. So if you want to have that discrimination, you have to set f by fg as 15 to 20. Did you understand by setting f by fg to 15 means what? Test frequency is 15 times the limit frequency. Okay. And if you want to use ECT for measuring the diameter changes, basically if some ovality is present or not, if you want to see, then you have to set frequency very high. It should be almost 100 times the limit frequency. Okay, so that is why how we use this limit frequency to determine what should be the test frequency, right? Next. Now, here I will introduce a concept called similarity law. So suppose you are doing a testing and you have optimized all the parameters, you have set, you have estimated characteristic frequency, you have set the operating point at the near region. Suppose you want, and you got a good sensitivity. Suppose you want to have identical sensitivity for another test object with another probe with another frequency. How to achieve that? So you can use the similarity law. You take first test condition. Suppose I am taking a thin walled tube. Okay. So my tube dia, thickness, frequency, resistivity, everything is fixed. And I have optimized such that my sensitivity is acceptable. Now that I want to achieve same sensitivity for another thin walled tube of different dia and different conductivity, you can use this law and find out the test frequency. Got it? So this is called similarity law. For example, I have to inspect one specimen, and that specimen is made out of some rare alloy, okay, or one expensive material. And for all NDT testing, you need some reference standard. Right? Without reference standard, you cannot do testing. But that reference standard, ideally, it should be from the same material, same load. But it is not available. What you will do? You choose another material which is of same geometry, but which is easily available. You make the calibration flows there, set the sensitivity, frequency, everything, so that it is operating at the knee point. Use the similarity law and translate it to your required thing. Then you can find out what should be the frequency and dia, everything, so that you have the same sensitivity that you achieved in the calibration. Right? So that is how we can use the similarity law in eddy current testing. So the same, it's slightly different for rods, thin wall tubes and thick wall tubes, but it is just that diameter, that part alone changes. Now, let us see how the impedance, so we are talking about impedance plane, eddy current signals and everything. So let us see how the impedance plane signal actually looks like for ECT. I think Arvind sir has already covered this. I'll just recap it once. So this is my impedance plane. So what sort of a probe is shown there? Can anybody answer? We have come across absolute probe, differential probe, transmit receive probes. What type of a probe is that? It is shown above the specimen, absolute probe. Because there is only one coil, right? So an absolute probe is used. Now I am keeping the probe in a defect-free location. And suppose this is the impedance point in a defect-free location, okay? Now I am moving the probe across the specimen. When the probe is coming near to the defect, it will start seeing the defects and the impedance is changing something like this, okay? And when probe is exactly underneath on top of the defect, the impedance change will be maximum from the defect-free region. And when I further move it away, it will trace back. And finally, when the probe comes back to the defect-free region, it will go to that point. So our typical impedance plane signal for a defect for an absolute probe will look like this. So that is what Okay, I have just gone in the ultra direction, but that is what is shown there. So now, so in this, this is a specimen having 3 surface defects of varying depth. Now, the test is conducted in the first scenario, test is conducted at 50 kilohertz. And I have moved the probe across the specimen, and you got, for the first defect, you got the red indication. Second defect, the middle defect, you got the blue indication. And the deepest defect, you got the green indication, right? Same test I performed. So you see, so in the first, in the last impedance plane you see, so for each defect, you can observe the phase angle of the signal is varying and the amplitude is also varying. So phase angle is nothing but, this is the phase angle. Basically you draw a line from this end to this end, and the phase angle with the negative x-axis we also always take. So this is the phase angle, and the distance, basically the distance between these 2 points is the amplitude. Okay. So the amplitude and phase angle changes. Can anybody tell why the change is happening like that? As depth is increasing, what is happening to the phase angle? The shallowest one is red and the deepest one is green. So as depth increases, phase angle increases. So why it is happening? Because when the eddy current is diffusing inside the material, the phase angle of the eddy current changes linearly. So that that parameter or that relationship we use for quantifying the depth of the defect, because it's a linear relationship. So that is why the phase angle, the signal gets shifted. But rather than phase angle, amplitude is also increasing from red to green. Why? Right. Volume is more. So that is why amplitude is increasing. Now you come to the second scenario, whether everybody can see that. I have increased the test frequency from 50 kilohertz to 300 kilohertz. Initially the test frequency was 50 kilohertz. The second case, I have just increased the test frequency from 50 kilohertz to 300 kilohertz. All the 3 defects are detected, but there is some change. There is some difference. Phase angle difference is more or less? More. Why? Frequency is higher. So when frequency is higher, what happens to depth of penetration? It will be less. So eddy currents are more focused on the surface, and all these defects are surface defects. So we will have good discrimination between depth of the defect at higher frequencies for surface defects, right? So that is why at 300 kilohertz the phase angle spread is more. So this is how you can optimize the test frequency. This is one way. Now coming to subsurface defect or inclusions, same coil I am moving. So 2 voids are shown here. They are like inclusions, A and B. One is near to surface and one is slightly below the surface. So we are getting 2 signals. I think already the things are shown here. So can anybody explain why it is happening like that? So subsurface defect B, which is further away from the probe, one small amplitude signal is there, but phase angle is maximum. Why? First we will take the defect or the void B, which is farther away from the probe. Its phase angle is maximum with respect to negative x-axis, but its amplitude is smaller. Why? First let us see why phase angle is more. Exponentially that will determine the amplitude, right? But why phase angle can be more? So phase angle increases linearly with depth. So void B is farthest way located from the surface, right? So its phase angle change will be maximum compared to all the other, right? And as he said, by the time eddy current reaches there, its amplitude will be small. So that is why the change in amplitude is small. Okay. Now come to void A. I think I am going too much into. Anyway, but understand that at least this much takeaway should be there. Phase angle is proportional to depth. Okay, so more the depth, higher will be the phase angle, and always we use phase angle as the parameter to quantify depth. Okay, fine. Again, similar example I have shown, but instead of surface and subsurface is compared. So let us see. Let us just take the three examples. Already the first example is already explained. So three surface defects are there. As depth is increasing, phase angle increases, as well as amplitude is increasing. So the first signal is for absolute probe. The second one is for that 8 pattern is coming. That is for which probe? Anybody can tell? Differential probe. There are two coils are there. So these coils, one will be clockwise, means the other one will be counterclockwise, so that you will always get a V1 minus V2. So you will get a figure of 8. So there also for a small shallowest defect you are getting a small amplitude and small phase angle, and deepest defect you will get larger phase angle and larger amplitude. But when it comes to a subsurface defect, you see we have shown two subsurface defects. One is only 0.7 mm below the surface. The other one is 1.5 mm below the surface. But you look at the impedance plane, means defect signal. 0.7 mm is having large amplitude. Can anybody tell why 0.7 mm is having large amplitude even though it is located only 0.7 mm below surface compared to 1.5? Amplitude is proportional to volume. So you compare both the defects. Which is having more volume loss? First one, which is 0.7 mm below surface. So that is why it is having larger amplitude. But it is only 0.7 mm below surface. So its phase angle is less compared to 1.5. Got it? Similarly for differential probe also. So amplitude is proportional to volume and phase angle is proportional to depth. Okay. Okay. Next. I'll just change the track. I will introduce one variant of eddy current testing called pulsed eddy current testing. So till now in conventional eddy current testing, we use continuous sinusoidal waves for excitation. In pulsed eddy current testing, instead of continuous sinusoidal wave, we use a pulse. Okay. So the advantage is that pulse will have, if you take Fourier transform of such a pulse, you will have n number of frequencies. You will have a primary frequency and its harmonics. So that means you will get information from all the frequency components. I think it is not there in the thing, but I can share the PPT. But it is available in the open literature. So for pulsed eddy current testing, the main advantage is that it has n number of frequency components. So you are getting information from all these frequency components. So another advantage is that the pulses will be of short duration. Okay, so we can give a pulse of very high amplitude. So we can have almost like a volumetric inspection. The major drawback of conventional eddy current testing is that it is a surface and near surface technique because of the skin effect limitation, right? Skin effect or because of the exponential decay of the eddy current. So eddy currents will be only focused on near to surface. But if you use PECT, pulsed eddy current testing, use a very high amplitude current for a short duration and measure the response. Because it is of short duration, the coil will not get heated up and you have n number of frequencies, so you will get information from all the full depth. Okay. So pulse ECT signal will look something like this. So in conventional ECT we have impedance, amplitude and phase angle, right? Amplitude represents the volume and phase angle represents the depth. So like that in pulse DCT we have again peak amplitude of the pulse which is proportional to the volume and the delay at which the peak is happening, the time delay or time to peak we call. So that is proportional to the depth or thickness. Okay. So the time information or the phase information is coming from the peak shift. All these things are available in open literature. I can share the slides also. Next. Okay. One major advantage of PCT is that this lift off intersection point. This can be used to make the testing insensitive to lift off. But you can, this is an observation. What you can see is whatever be the lift off for a particular test specimen parameter condition, always the signal will cross over at a particular point. So if such a thing is happening, then you can ensure that specimen parameter is not changing. But if the LOA is shifting from that point, then you can understand that it is happening due to some change in specimen parameter, not due to lift off variation. So this is when lift off, whatever be the lift off, always the signals will cross at a particular point. And that point is only governed by the change in specimen parameters. So if that LOA is getting shifted in our measurements, so that indicates that there is a change in specimen parameters. It can be defect, it can be conductivity change. But it is not due to lift off. Lift off is always one disturbing variable which is always happening in the ECT. So LOI, we can make use of this LOI to make it independent to some extent, to insensitive to lift off variations. One of the major applications of ECT is to detect corrosion under insulation. So most of the these pipelines and tubes will have insulation, and there will be a clad to protect the pipe because mostly they will be ferromagnetic. And in order to detect corrosion from clad itself, no need to remove the aluminum clad. From top of the clad itself, you can detect what is the condition of the tube underneath just using PECT. So this is one of the major applications. Another major application we use in marine explorations to check the healthiness of the structures erected in this sea environment. This is another application of PECT. So because of lack of time, I just sped up. So just to summarize, we have gone through the distribution of eddy current, what are factors that affect, influence the ECT testing, how to set the frequency of testing so that we have good sensitivity for plates, for tubes, and we have also seen a variant of ECT called pulse ECT, how it can be used for doing thick volumetric inspections. So these are some references. The first reference is very good. It covers almost all electromagnetic NT techniques. And if you want to focus on ECT, you can go to the second reference. Who is interested in more mathematical things, and if you want to explore in that way, you can go to the second reference. Thank you.
Suppose there is a pipe of 10 meter length and that pipe is carrying some viscous fluid and there are some depositions inside the pipe. Can we determine where exactly and how much is the deposition with the help of this technique?
ID is accessible or?
OD is accessible.
Yeah, we can use it. As long as the deposit is non-conducting and magnetic, if it is a non-conducting and non-magnetic deposit, we can always use the technique.
Suppose they are paraffins, like they are carried in petroleum oils.
The fluid doesn't matter as long as fluid is not conducting.
Okay.
It can be any fluid. It has to be non-conducting and non-magnetic.
Okay.
But even if it is conducting, we can optimize parameters so that we can limit the frequency so that eddy currents are only there in the wall thickness. We can do.
Thank you.
At the start of the lecture, you just show that if there is a small defect, the how patterns will be there.
Right.
But what if there is a broader and longer in length,
Right. Yeah.
which cannot be, which should be detected at any cost?
So pitting will be usually localized. Localized indications will have a clear pattern like what I have shown. But if it's an extended, you will get indications at both the ends. But if you are using an absolute coil, you will get a signal something like this. But if you are using a differential coil, you will get something like this. So at the extremities of the indication flow, you will get indications. In between, because it's a differential coil, it will get cancelled out. Otherwise, for an absolute flow, you will get it. So that is why I told the dia of the probe matters. Dia of the probe should be at least the length of the defect. If it is less than, if the length is less than the dia of the probe, we may miss it.
So thank you very much, Arjun, for a very good lecture. So from ISNT Pune chapter and PFMB. So now I invite TSVR Nageshwar Rao, Scientific Officer F at NFC, Nuclear Fuel Complex. He is a dedicated electronics engineer specializing in maintenance of NDT and mechanical testing equipments within QA plants. Renowned for his expertise in electronics and its methods, he consistently delivers excellence in efficiency, productivity, and innovation. Sri Rao has played a pivotal role in advancing technology by indigenously designing and developing PC-based NDT systems. These systems not only modernize test facilities but also serve as import substitutes, showcasing the department's self-reliance and technical acumen in creating specialized equipment for testing nuclear-grade components. His contribution underscore a commitment to enhancing throughput and integrating cutting-edge technology into critical applications. For his educational qualifications, he has obtained his Masters in Embedded Systems from BITS Pilani and received NDT Award 2024 for NDT Systems Innovation and Development. Over to you, Nageshwar Rao. One more announcement. After this lecture, we will have lunch and then come back.
Very good afternoon to all. Am I audible? थोड़ा ऊपर okay. So first of all,
thanks Arsu sir and ISNT Pune for inviting me to deliver this talk on advances in ECT instrumentation, and also thank our previous speakers for having introduced the basics of eddy currents. That makes my job a little bit easy, because my concentration in this lecture is basically how to understand the instruments, because once you don't understand the capability of the instrument, you cannot operate it properly. So though you have a theoretical background of how eddy current works, but unless you understand the nuances of different controls in the equipment, then like for example, if I can put you like a simple example. Now we are all carrying a very modern cell phones, but not even 10% of the functions we don't understand, right? So like that, if you can understand, that's a beautiful device, cell phone. If you understand, you can do many things. So similarly, if you understand the basics, at least basic controls of eddy current, then you can use the beautiful technique of eddy current for many of our NDE examinations. Next. So the outline is a brief discussion on electricity, magnetism, eddy current propagation, and then comes to equipment and understanding the equipment parameters. This is the basic my outline of today's lecture. Thanks. So all this starts from Faraday's laws of electromagnetic induction. That is the starting point. So where the Faraday has found that an alternating magnetic field, or rather I put like the relative motion between the magnetic and the conductor gives rise to some induction in the material under test. That is the basic. And if you can read that a voltage induced in a circuit whenever relative motion exists between a conductor and a magnetic field, and the magnitude of this voltage is proportional to rate of change of thing. So this is all theory, right? So how do we understand these electromagnetic induction is completely given by the beautiful 4 Maxwell's equation, which governs the electromagnetic induction, eddy current technique, everything. In the 4 these important equations. The first law is Ampere's law, and the second law is Faraday's law, which is the induced EMF del cross E. That means the EMF revolving. When you say cross in these operators, cross and dot, there are 2 operators. Cross means curl, that means which revolves around is proportional to rate of change of magnetic flux, dou B by dou T. So which is revolving. These currents are revolving. So that's why we call them as eddy currents. So because they are circular in nature and they try to move around, if there is an impediment or if a crack occurs to the eddy currents, then what they do? They cannot cross over. So they try to move around and complete the path, right? So that is where they are called eddy currents. Not because they are wasteful currents, because they try to move around, they are called eddy currents. So and another law is the direction of induced EMF is opposite to primary cause of it. It tries to oppose it. So whatever is changing, it tries to oppose it. So these are the 2 governing rules where the gamut of eddy current testing is complete. Next. So I would say eddy current or electromagnetism, if you go in quantum physics, it is a wave. Current is also a wave, right? If you can see in the animation, there is a direction in which the wave is passing in this direction, right? And you can see there is a variation of the red is the electricity or electric field, and there is the blue is magnetic. They are orthogonal. They are in opposite 90 degrees direction. So once you call anything as a wave, there are 2 things that happen in a wave. It is a physical wave, means mechanical wave, or electric wave. The 2 things that happens. The equation is given, but I'll try to make it very simple. that the wave, once you call it as a wave, it will have attenuation. Because you see, I am speaking, means I am generating a mechanical wave, sound wave. It goes to the far end, its intensity comes down because of the attenuation. So when I say anything is a wave, it will have definitely the attenuation will happens. And also there is a phase change. Definitely these two things, when you call it as a wave, the two things is, one is that it will have attenuation over the period of time or the distance, and it will have a phase change when compared to the starting point, there is a phase change. So these two governs the eddy current test principle. Okay, next please. Yeah. So we have introduced in the previous lectures that it goes down, intensity comes down, the whatever right now I told, it is pictorially represented. If you can see the left figure, on the surface, if you see, there is a maximum current density. Maximum eddy currents are concentrated on the surface, and as you go down the material, what is happening? Their intensity coming down because of what I said, attenuation, because of a wave, right? So we call it as a stand-up depth of penetration, that where the eddy current density when compared to the surface, if it comes to 30% or rather 37% of its maximum at the surface, we call it as a SDP, stand-up depth of penetration, right? And then also, since it is a wave, there is a phase lag, right? So the phase lag, what I would say, it is generally, it is a 57 degrees or 1 radian at one skin depth, whatever we calculate. Then there is a equation, if you can see on the right side, JXJT means the current density at time domain and the distance, if you can see, it is multiplied by e to the power of z by delta. Means that is a minus sign, means it is dividing it. Means your eddy currents are getting reduced. And there is also, if you can see, minus z by delta. Means it is happening, the phase is also is changing, right? So these two information, if you can see the how much variation in the amplitude and how much variation in the phase, if you can measure these two things, you can understand the size of the defect, you can understand the location of the defect, right? Next please. So I would say, people say that it is a phase changing. How do we visualize the phase changing? You can see in the right side figure, you can see the first one and the second one. One thing is little bit offset to the right? So that is what phase change in electronic terms. Being an electrical engineer, I little bit introduced to electrical terms as well, right? So the phase change is the wave, it is getting an amplitude, it is little bit reduced, as well as it shifted little bit. So if you can understand the phase difference, now you will understand the distance or the location of the defect. Next please. So this is also introduced, but again just a recap, only the take home is the discontinuity is least detectable when its longest dimension is parallel to eddy current. The longest dimension, I would say, the second, you see there is a longest dimension, it is in vertically, right? So that's longest dimension is in fact is a parallel to your eddy currents. So it is least detectable. Whereas if you can see the third figure, the longest dimension is 90 degrees to the flow. That means that is easily be detected. Okay. So this is the simple principle. If the longest dimension is parallel to the surface, parallel to the eddy currents or orthogonal to the eddy current, that only decides your sensitivity of the testing. Right? And also the right side, you can see the edge effect, where eddy currents are much disturbed at the end. So even though there is a defect is there, you are not able to detect because they are masked by this edge effect. That's why we say that around 1 coil diameter or 2 coil diameters, we generally say that the sensitivity is less because that is more masked by your edge effect thing. Next please. So these are the various things that can be detected. The conductivity, permeability, skin effect, edge effect, all these things already been introduced. We can see all the thing comes to only single formula. The previous lecture you have seen so many formulas, 4 or 5 formulas, right? So they are very important. Once you go into the practical testing, But to understand eddy current, there is only one single formula from which all other formulas comes from. That is delta is equal to 1 by root over pi f mu sigma. So anyway, pi is the, it's a constant. So the depth at which eddy currents are appreciable decided by the frequency, decided by the permeability, decided by the conductivity. That means these three things affect the eddy current sensitivity, correct? So that means what you can detect with eddy currents? You can detect permeability, means whether it is a material is magnetic or non-magnetic, right? So that is what is called material sorting, right? You can able to sort it out, whether it is a magnetic material in a primitive sense. If not even one type of material, even though in the conducting material, non-magnetic material also you can segregate, but simply say ferromagnetic or non-magnetic, simply by mu. And there is another type, sigma. So that is what is called conductivity of the material. So that also affects your eddy current distribution, eddy current, all this phenomena. That means you can do the conductivity measurement as well. Okay? And of course, once I say conductivity, if there is a defect is there, definitely localized variation in the conductivity will be there. So definitely it gives rise to some signal from the eddy currents, correct? So like this, the conductivity, permeability, all these things can be detected with the only one single technique. That is the advantage and disadvantage and disuse also, I would say, because too many parameters are mixed up, because you never know what parameter really made the difference. Unless you make other parameter constant, you cannot say, right? So you are doing something like a conductivity measurement, suddenly other type of material has come, so you don't know, because it will give rise to similar signal. So you have to make other parameters constant and then check for the other one. That's what the previous lecture you said. You decide on PZ, that is one characteristics frequency where your known conductivity gives the maximum signal, other parameters are minimized. So that's where we select the different frequencies depending upon. Next please. So now, having introduced the basics of eddy current, what are the parameters that are making a role in the eddy current, like conductivity, permeability, frequency. Now let us go into the actual topic, the eddy current instrumentation. So what does instrumentation mean? Eddy current instrumentation comprises of just the equipment, the probe, as well as a reference standard. These three make an eddy current instrumentation, not just an instrument. Unless you select a proper probe, your testing is not complete. Unless you select, because this is a comparative measurement, eddy current is not absolute measurement. It basically is a comparison measurement. Unless you have proper standard, your testing is not complete. So these three makes the complete of eddy current. So once we say coil, already it is introduced. So coil will have resistance, coil will have inductance. Basically once you wind a wire in number of turns, it becomes a coil or a solenoid, right? So generally we understand that once you understand, it will have inductance, right? Magnetic property. Okay. Because our intention is to make a coil of inductance only, but resistance is already implied because you make with a wire. Wire will have certain its own resistance. So definitely every coil will have a DC resistance, which is only resistance in all things. Either you give AC or DC, it is equal. But the thing changes once you give AC current instead of DC current, things changes. Then your inductive parameter comes into picture. That's what we call inductive reactance. It is also opposition. Resistance means opposition to the flow of current. Inductive reactance is also opposition to the flow of current, but only AC currents. DC it doesn't work, right? So there is a formula R plus JXL. That's where we represent. R is the DC resistance of the coil plus the XL, which is nothing but 2 pi multiplied F into L. So that is the inductive reactance. So if you represent in a rectangular form, it is R plus JXL. If you represent in a polar form, it is Z angle theta, where it is given Z is square root over R square plus XL square. and tan inverse something, whatever it is. So ultimately what it boils down is we have to maximize the impedance, we have to maximize the inductive reactance, limit the resistance, because resistance is altogether waste. Once we say resistance means it is the energy wasting component. Energy is dissipated. Huh? At home we have heaters, right? Geysers are there. What they do? So we will give current and they will get heated up. Means your energy is wasted as a heat that we are using as a boiler. It means once you say resistance, it is an energy dissipating component. It is a waste. So our aim should be, once you select a coil, the resistance of the coil should be as low as possible, the inductive reactance as good, as high as possible. So generally, so if you can say the figure of merit, which is nothing but inductive reactance XL divided by the resistance of the coil. So it should be around, if it is 10, it is a very good coil, right? Next. So how to make a coil? Now we understand, okay, if you wound a wire into coil, so it becomes an eddy current coil. It will exhibit the properties of magnetism, electromagnetism, whatever it is, so on and so forth. So what is the formula? So there are various formulas in literature, but most effective formula which I have taken from ISNT study material is given like this. Okay. So based on this, nowadays regularly this is an art as well, science. So how do you wound coil? What is the length of the coil? So based on all these parameters, what is the inductance required? So there are various parameters: the radius of the coil, the width of the coil, the thickness of the coil. Based on that, you will get this formula. Anyway, you have that material. You can read what actually it is. Okay. So ultimate thing is you have to maximize your inductance, minimize your resistance. That is the main thing. So if you want to have bigger inductance, means you will have n number of turns, because the inductance is proportional to number of turns squared. N square is there, no? L is proportional to n square. So you should have more number of turns. If you have more number of turns, your coil wire should be small, wire thickness. If coil wire thickness is small, resistance increases. But your aim is to decrease the resistance. So these are contradicting things. So you will optimize the thing. That's why nowhere in literature nobody will tell how he has made a coil. Formulas are there, but you search in and out in the literature, in textbook or manufacturers, nobody will tell how he has made a coil, because that is art. That is where he gets the money, right? Next please. So now, you are introduced in the previous lectures, absolute coils are there, differential coils are there. So how in an instrument, how they are connected? We know the advantage of absolute coil and differential coil, right? Absolute coil means basically a single coil which generates the eddy currents or electromagnetic induction, which also senses the material properties. That is what is called absolute coil. Single coil does the same job. Okay. So this is how they are fit in the equipment. You can see the first figure. There is a R is there, resistance, and coil is there. So that coil, the square box is your test sample. So if material is not there, it will have its own intrinsic impedance R0 plus JXL0. The would say if I am going little faster, just stop me, because last of time I am going little faster. But if you are not following me, just stop me. Okay. So the impedance of the coil Z is equal to R0 plus JXL0. Okay. So this is the DC resistance of the coil, and this is the inductive reactance. This is a coil. This is R0. This is JXL0 of the coil. Now if I measure, if I put a voltmeter across it, okay, If material is not there, it will have its own R naught plus J XL naught. Okay, some voltage will be induced, right? If you measure a voltmeter over here, right? Now, if I bring my material over here, so because a material, a conducting surface is near the coil, eddy currents are in, because electromagnetic induction happens, eddy currents are induced in this. Okay, this eddy currents will oppose the primary field because of the Lenz law, right? So when I say, see, the single thing is, electricity and magnetism are not separable, I would say, as far as eddy current is concerned. Once you say there is a magnet, in terms of eddy current I am telling, once I would say there is a current, there is a moving electric charge. So there is always associated a magnetic field around it, whatever it is. Posted, that is the first person who got it. So once there is a current is moving, so moving charge produces magnetism. Moving magnetism produces electricity. Both are reversible phenomena. Because alternating magnetic means it is a moving magnetic field, right? If you give AC current to a coil, it will generate alternating magnetic field. So alternating magnetic means moving magnetic field gives rise to current. Moving current gives rise to magnetism. Both are things. So once I say I put a material near to this coil, eddy currents are induced. So once eddy currents are induced, there is already a magnetic field, that what we call generally is a secondary magnetic field, right? So this secondary magnetic field will try to oppose the primary magnetic field, means it weakens the magnetic field. Okay, so the net magnetic field is reduced. This statement everybody agrees? Once you bring a material near to the eddy current coil, the net magnetic field is reduced, correct? Because the secondary magnetic field due to eddy currents will oppose the primary magnetic field, correct? So what is happening? That means magnetic field is weakened, means my XL component is reduced, because this is what magnetic component, no? In this, to simply put it. So my XL will reduce because my magnetic field is reducing, correct? So what is happening to my resistance? Does it change or not? Just keep this question in your mind, we will come to that. Okay, just think over what happens. Okay, now so there are 4 varieties of general eddy current coil configurations are there. First is the typical single coil bridge, where single coil is generating magnetic field. If something is happening because of the material, this is changing, so finally my Z is changing. Okay, so by changing the Z means here Z is changed, my voltage is changed. So initially, for example, I put a meter, a big meter here, where it is, my needle is at the center. Okay, when material is not there, when material has come, okay, because there is a change, it will deflect either way. So it may deflect either way or this way, whatever it is, but definitely will deflect. That means I am able to say that whether material is available there or not. Correct? Now once I know the material is available, then again I do adjustment of some control, again I will bring back to here. Okay, I balanced it. This is what is called, we call it as a balance. So material balance, air balance, then I made it a material balance. Now in the material, now I have a defect. Okay, so what is happening? My eddy currents cannot cross over here, so they try to go around this. So my eddy current path length is changed, is increased. Correct, na? So path length increased means what is happening? Resistance is increasing. R is equal to rho L by A. My eddy current path length is increased. Okay, what is happening? Resistance is increased. So what it is doing? A number of eddy currents are reduced. Correct, na? Because the opposition is increasing to eddy current. So my eddy currents are reduced. That means again there is a change in coil. Again there is a change in the coil because of the defect in the material. So once there is a change in the coil, again my Z is changing, correct na? So that means again it will not be the balance point, it will move either way, correct? So that means I am able to now identify in the same material whether defect is there or not, correct? So that is what the eddy current detection altogether. How we are able to doing? I am just sensing my coil, its impedance, I am just balancing out, and from the good material, if there is a bad material has come because of the defect, inclusion, porosity, whatever it is, some flaw is there, what is happening? My impedance of the coil is changed, and that change is reflected by a deflection of simple material, if you make it very simple, right? That is all about eddy current testing. And then comes here only we are concerned about only the amplitude, correct na? But there is another parameter is also there, that is phase. So there comes the advanced instrumentation, not just amplitude measurement. If you measure the other parameter as well, the amplitudes as well as the phases, how it is affecting, if you can measure that phase as well, then your eddy current principle is, testing is complete. So you find the defect, you find the where is the defect, correct? Quantification and location. So totally you are measuring the equipment. So the second figure is a balance. Generally in electrical engineering, people you might have studied, or in your high school physics, Wheatstone bridges, right? So Wheatstone bridges are used for measurement of even small changes, not big changes, even micro ohm level changes. Small changes also Wheatstone bridges can measure, right? So here we are just transforming it to a bridge form, where you can see the bridge is balanced. The top two are the known fixed resistors, and the bottom is your test coil, and the other impedance is a balanced impedance, which is almost equal to your coil impedance. Then the bridge is balanced in this condition. If I write okay. So this is the AC signal I have given to the coil, and I put just a meter over here. Okay. So the bridge is balanced if this Z1, Z2, Z3 and Z4. So the condition is Z1 by Z2 is equal to Z3 by Z4. The actual value does not matter, but the ratio only matters. Okay. If these two are fixed resistors, equal resistors, and this is my coil and this. So once I put my material near to the coil, there is a disturbance. I will adjust this resistor in such a fashion my meter deflects 0. So again I achieve this condition. Now whenever there is a change in this because of the material defects and all, there is an imbalance. That imbalance is shown as a deflection of the material. So here the advantage when compared to the first one to the second one is, first one is very gross level changes it will measure, and the second one even the micro level changes it measure. In fact, if you see the eddy current, only 1% change only you will get. You understand? Eddy current, the disturbance is not more than 1%. So if you see, you are giving 10 volt signal, only the disturbance due to a defect, a very big defect, okay, or a defect through and through defect, it is only gives rise to how much change? 1%. So that much small changes can measured by only by these kind of devices, the bridge fashion. So the third one is also similar the thing, and fourth one is a differential coil arrangement. Okay. So you can see that they both are test samples. If there is a differential coil is there, both will see the reference sample. If defect you are, I think he has already shown one figure. Maybe we can see in the other figures as well. So this is how mostly 99% of all our probe measurement is this kind of measurement. What is it? It's a bridge fashion measurement only we will do. Okay, next please. So there are other, you can see differential. You can see the middle figure. It is again a bridge fashion. Okay. So both coils, if it is both are seeing good material, they will develop equal voltage across them, and the difference of voltage is 0. So whenever there is a real change compared to one coil to the other coil, that will be detected in the differential coil. That's why we say that differential coil is most useful when you want more good sensitivity, kind of like a small defects. If you want to measure, go for the differential coil. Okay. And there is another type of measurement as well, which we call transformer or send receive or reflection measurement. It works like a transformer. One coil is given. It is not a bridge. Okay. The other coil is a pickup coil. One is a sender coil, other is a pickup coil, send receive coil kind of thing. Okay. Next. So these are the different types of probes. You can see somebody asked whether we can do welding also. If you can see, that is the probe used for weld measurement only. The first one, the figure, surface probe, where you are measuring on the surface by moving across the sample. Okay. The arrangements, they will be spring loaded because you need to make that lift off as minimum as possible. So they will be spring loaded so that you can apply the constant pressure maintained. And you have ID bobbin coil where the material, your test coil goes inside the material, and you have encircling where your material, your coil encircles the material. That's why we call them encircular OD coil. Next. So this is where encircling coil, you can see the defect here is very longer defect, longer than your length of the coil. Okay. Then what is the disadvantages? You may miss the defect, or you may say that you detect only the ends. Even though there is a very big defect, but because of the differential coil, you will see the only ends are detected. Because why? Because if you see, this is a longer defect and two coils are there. Both coils are seeing the defect area. Because of differential measurement, altogether differential measurement, what it does? It will see the only difference of them. This is seeing the defect, this is also seeing the defect. In an effect, nullified. So what you are going to detect? You are going to detect this end and this end. So that is the disadvantage with the differential coil. But if such a big difference is there, where you are going to miss the defect, or sensitivity is becoming low, why we have a differential coil? Because see, any type of testing, NDT testing, depends on what type of defects you want to measure. If your manufacturing process is, creating longer defects, then you should not use the differential coil. You have to go for the absolute coil. Okay. So our testing methodology based on our manufacturing process only. There is no one good technique for any type of defect or for all type of defect. You have to optimize. Your manufacturing process is a very good process, and sometimes only pits or small defects are there, then you go for eddy current differential, right? Next. So these are all advantages and disadvantages. So basically you can read it across. The main thing is that the differential coil is less sensitive to the temperature variations, environmental variations, okay, and drift, all these things, but only for abrupt changes, not for the longer defects, longer than your coil. Okay. Next. So now we understood what probe does. Then how do we select a probe? What are the parameters that an engineer or a NDT engineer should keep in mind in selection of a probe? The probe is, first thing is material penetration requirement. Are you interested in the total bulk of the material or surface of the defect? Because bulk of the material, there are other tests like ultrasonic and radiography. Eddy current excels well for surface and subsurface. But if you want to measure 3 mm or 5 mm block with eddy current, it is not a good decision, right? So whether you are concentrating on surface, okay. So that is the first one. Then sensitivity. What type of sensitivity? I told you, no. If there is a small defect, go for a differential. Okay. Generally, the length of the defect should be less than the coil width. So generally, we get in commercial, or if you go to the market, you will get coils of generally 2 mm, around 3 mm coil width will be there. Less than that, nobody is doing. So you cannot have a bigger defect or small, smaller, depending upon that limitation you have to play with. Here and there, little bit, 10-20% here and there will be done. Okay. Then type of probe connections, because your probe may be coming from USA, it is having a different connector, but your equipment is having only 4-pin bobbin connector. How do you do? Many times it happens. Technophore manufactures 2 types of probes. Encircling, I think everybody knows Technophore, no? Technophore is the eddy current manufacturer in Pune only. He supplies all over India and abroad as well. Okay, so he has 2 types of connectors, 4-pin connector and 7-pin connector. If you don't understand what it is about, that coil cannot be used, or other coil from other manufacturer you cannot connect it. So the knowledge of what type of connector, so that is also makes it very important, because sometimes you will be fixed. You have to use that particular probe of that manufacturer only, right? Then, yeah, the very important thing is impedance matching. So most of our equipments, our probes are designed for 50 ohms impedance, most of the probes. But some equipments can tolerate here and there. Okay, so the disadvantage is, the electrical engineering says that you will get best signal when impedance matches. If your equipment is 50 ohms based equipment, you put a 50 ohms coil, you will get the best sensitivity, right? If you put 200 ohms coil or vice versa, your sensitivity gets down. So understand this principle as well. But nowadays digital equipments are so tolerable, even 200 ohms connecting to 50 ohms also will do. But good old days, some 20 years back, this is a very strict phenomenon, because inside electronics is designed such that it works for that particular probe only. Nowadays, the digital equipments are more tolerable. Right? Next. So now comes to instrument. We understood different probes. Now comes to instrument. So if you can see the left side figure, the oldest equipment I have seen, it was something like 1970s. I don't know how many of you have seen. It is a CRT based equipment, and also a storage oscilloscope. You will have CRT, the trace is visible, and you used to have one control to balance. If you press the button, inside one motor will rotate, it will alter that resistance, and finally somewhere the point is there that slowly comes down to the center. So from those equipments to nowadays credit card based sized equipments, the electronics have grown. Okay, we will see how they have grown. Next. So the equipment is completely as there is a signal drive and your coil. Then there are various the digital phenomena is there, where balancing, detection and oscilloscope are different types of recorders, CRT screens, computers, and if it is an automated testing, you have a tube handling or bar handling mechanism as well. So this all makes a complete equipment. Next. So the equipment we can classify as monoparameter, means equipment is designed for one particular type of measurement, like conductivity measurement, okay, or like flaw measurement. So those are called generally monoparameter. Then like track detectors or flaw detectors. So they don't do much of the analysis, like phase analysis, all these things they don't do. Just they measure the impedance change, how much it is changing, and they will display, just like I told you like this. So if crack is there, it moves. Or if it is a digital equipment, it will give some number, numerical value. Okay. Then there are the older methodologies like ellipse, time-base, vector. Next, please. So I'll just introduce you, though these equipments you never find. Next, please. So this is what is called ellipse method, where those equipments, you can see if it is a straight line changeover, so it is basically a conductivity variation. If the circle is forming, ellipse has not a single line, opening of is there, that is something like conductivity, other one is dimension, and the angle and both are changing, it is like both are changing. So basically, whether dimension is changing or conductivity is changing. Okay. So these type of equipments earlier they used to be there. Next, please. This is something like phase analysis measurement, where I told you, no, the phase changing means the wave is shifted. So they will adjust one slit on the oscilloscope. Instead of seeing total oscilloscope screen, they will adjust some slit where the important parameter is monitored. So they know that if conductivity variation is there, it will come, the point comes over there, so they will put the slit over there. Okay, they will see. If nothing is there, point will not be seen. So those equipment. Next please. So you can see the direct conductivity 30 ICAS, percentage of ICAS, as well as thickness, all these things you can see. Next please. Yeah, the latest equipment, all from the last 20 years and so forth, all are digital computerized equipment where impedance measurement is seen. So it is called impedance plane, where I told you, know, the coil is having resistance as well as inductive reactance. So if you can, in a coordinate, you can do R and XL, so it is called impedance plane. The impedance of the coil is measured by comparison measurement, right? So if you know, for example, Z0 at air, some R0 plus JXL0, that is what the coil, so somewhere it is here. Okay, let us think it is having some R0 and some XL0. So my point is here. Okay, now to this coil, okay, I brought a material here. Okay, so what are happening? So the magnetic field is cut by this coil, then I have eddy currents induced, correct? So these eddy currents will oppose the primary magnetic field. So what is happening? My inductive reactance is getting down because the total magnetic field is reduced. That means my vector point tries to come down because my XL is coming down. Okay? This for everything is clear now? Now the very important thing comes. What happens to R? I introduced and I stopped it there half an hour back. Now I am going to tell you. So simple, I told you, once you say resistance means it is an energy wastage. This point clear? Once there is a resistive component in any electrical circuit, it is an energy wastage. Correct, na? Now, because in my material, eddy currents are reduced. Correct? So do I require eddy currents? In fact, I don't require. Why do I require? But I cannot stop them, isn't it? They are induced because of the electromagnetic induction. So because here eddy currents are induced, is it a wastage or not? It is wastage, no? Because I don't want, but I cannot stop. They are, by inherently they are getting induced. So somebody is moving, electrons are moving. That means your energy is wasted. And who will compensate? For example, I draw from my ATM card some amount. Okay, that should reflect somewhere, no? Where it will reflect? It will reflect in my bank account statement. Your amount is reduced. Here I have drawn some energy. This material is drawing some energy by producing eddy current. That will reflect. Where it will reflect? It will reflect on the primary coil. How it will reflect? As energy waste. So energy waste means resistance increase. Correct, na? So my primary coil resistance increases, my inductive reactance decreases, means R is increasing. This is all about primary coil, because we are measuring only primary coil, no? We don't measure anything on this material. Everything is on this coil, right? That means this is coming on this. So my point comes over here, correct? So this is material balance. This is how it is represented. Okay. Now in the material, there is a defect. In the material, there is a defect. So eddy currents tries to go all around all these things. So number of eddy currents are reduced or not? Because of the defect in the material. Eddy current reduced, no. That means my energy loss is reduced. My energy loss is reduced. That means R will reduce, because less eddy currents, less opposition. So that means if in the good material suddenly there is a defect is there, my vector point goes towards air. This is where it is. Okay. My point is tries to go here. That is where you can see in the figure, from air it comes down to aluminum, and if a crack is there, my point tries to go up towards the air point. This is how we interpret the impedance plane diagram. Okay. Next please. One second. Okay. So what happens for a magnetic material? So from air point, what happens to the magnetic material? If the ferromagnetic material is there, because of the ferromagnetism, my XL increases, because there is a magnetic dipoles, all these things are there. So it goes upper. Instead of going down, it goes upper. RL increases, R increases, but XL increases, and from there again the same thing happens. Okay. So the take home here, there is a formula given. Instead of going completely, you can see R coil R naught plus something. Whatever the plus, you don't remember. So what is happening? Once material is occurred from air point, so R plus something, XL L minus something. That is simple equation. Okay. So that's where it comes from top to towards right side. Next. So this is the complete equipment. Next. So this is the basic eddy current, inside what actually is happening. So there is a detector is there. In electronics we call it as phased detectors are there, or locked amplifiers. Okay. So where you divide the total Z component change as a resistive component as well as inductive component by using digital signal processing techniques. Okay. So it's a completely altogether different electronics phenomena, where you will get one resistance component and one XL component, that is plus. Next please. So then we have multi-frequency equipment. Already you are introduced why multi-frequency is required, because there are support plates are there which gives rise to very big signal because of some fitting or fretting or magnetic deposits. So what we do, we use another frequency, okay, where it concentrates only on the other unwanted defect. So unwanted and this original frequency, both are mixed as a subtraction. So the unwanted things will be removed. Okay, next please. So generally multi-frequency equipment means the last one, where you can see there are number of sine waves. One, for example, 2-3 frequencies are there. They are mixed in electronically. So one principal component and multiples of different components gives rise to this kind of thing, simultaneous frequency. Next. So how do you understand an eddy current system? What are the important parameters? So what is the frequency range? Generally in industry we write from 50 kilohertz to 400 kilohertz we use. And then impedance, I told you, generally 50 ohms to 200 ohms available. Number of channels, whether it is able to do absolute as well as differential, both arrangements it is catered to. Then number of frequencies, I told you multi-frequency equipment, number of frequencies. Then injection simultaneous, and the gain, because I told you only 1% or less than 1% change is there, but that needs to be amplified to such a level. So how much gain it is offering. Then sampling rate, because in automated testing, eddy currents are known for the highest testing speed possible. Like ultrasonic, we go maximum of 8 meters, 10 meters. Eddy current easily you can pass 20 meters per minute. So at that testing speed, in the digital equipment, are you able to digitize that fast or not? So that sampling rate, nowadays, every equipment is around 10 kilohertz is readily available. Okay. Then data rate. So how much data is stored? Because nowadays all digital equipment, all this data is stored in computer, right? You cannot sample, even though you are sampling at 10 kilohertz, you cannot store that much big amount of data. So there will be a digitization rate will be there. So generally ASME standard says that you should have one data point for every 0.8 mm movement of the tube or your this thing. Okay, so that comes down to around minimum of 400 samples if you test something like that. Okay, then to optimize, because eddy current, many parameters are affecting your localized conductivity variation, permeability variation, and dimensional variation. All these things affecting the eddy current output. So to optimize the signal to noise ratio, so we use different kinds of filters like low pass filter, high pass filter, whether your equipment is capable of offering those kind of things or not. So and data resolution. So ASM again standard says that minimum 12-bit electronic EDDY converters are required. So these are all equipment parameters that one has to be very careful in selecting or purchasing an equipment, because you bought an equipment but it doesn't serve your purpose. Then what is in fun? So understand the things, the capabilities of the equipment, so that you will choose the best equipment for your this thing. Next please. Next. So then reference standards, because I told you eddy current is all about reference, it's a comparative equipment. So you need to have a reference standard which is of same quality, same surface finish, same heat treatment, same dimension. All these things should be there. Same dimensions, same quality, same heat treatment, same cold working, same surface finish. Or else you are not comparing. You are comparing apples to oranges. Okay. Next. So this is thickness gauge and non-conductive coating gauge. Next. Little faster. Next. So this is how the equipments have changed. Next. So the how it has come from vacuum-based equipment to nowadays pocket credit card size equipment is because of eddy current or electronics advancements. So that gives rise to nowadays the smallest size possible. I am not going to deep into this. Okay, next. Next. So in addition to the normal probes, nowadays we have eddy current array probes. So where if you want to test a material, you have to move your probe across left and right in a raster fan. But using an array kind of this probe, in a single go you can inspect the more area. That is what is called eddy current array. So these kind of is nowadays prevalently available across many manufacturers. Next. So this is how it happens. Next. I think this is covered. Next. 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 So eddy currents everywhere, induction stoves, wireless charging, many where magnetic levitation also eddy current can be used. So these are other variations or applications of eddy current. So we have covered the eddy current propagation, different kinds of probes, coils, and different types of ECD equipment and their important parameters that one has to be kept in mind. Next. Thank you.
so thank you very much, Mr. Rao, delivering this.
Thank you, sir.
We will break for lunch and quickly we will come back by 2:15, 2:30. Because 2:15 to 2:30.
Okay. Let me try one thing. I actually joined through the Teams browser thing. Let me try joining through the Teams app. Maybe it'll be better. Just give me 1 minute. Can you can you hear me now? Yeah, let me see if I can share now. Um, is it full screen now? Okay. Yeah, sorry for the delay. Yeah. Okay, sure.
So thank you very much, Dr. Aparna, to join online. I think this is the first time that we are doing it YouTube live also and online. I don't know. It is a tricky thing, but let us see how it happens. But I think everything is fit and fine. I should introduce you now. Dr. Aparna C. Shilavadde is a principal engineer at NDE lab in GE Aerospace Research, Bangalore. She has been with GE and GE Aerospace Research for close to 20 years and has worked on design and characterization of different electromagnetic sensor systems and in the development of associated algorithms for inspection and monitoring applications in aviation, renewable and oil and gas sectors. Prior to GE, Dr. Aparna worked at Western Digital Corp and read write in Fremont, CA, USA for 3.5 years on GMR sensor design for hard drives. Aparna has a PhD from Carnegie Mellon University, USA, MS from Indian Institute of Sciences, and BTech from College of Engineering, Trivandrum, all in ECE. So I introduce Dr. Aparna. Over to you, Dr. Aparna. The stage is yours.
Yeah, thank you very much for the introduction, sir, and thank you for inviting me to give this talk. And I also apologize that I could not be there in person. I had something here in the office for which I had to stay back. So that's why I had to do this online. So hopefully next time I can come over. Should I get started? Okay. So I saw the agenda. Looks like there has been sessions on basics of eddy current, and so I won't go into that. I'll directly jump into some of the applications that we look at in the aerospace industry. So I'll start with a overall view of what happens So if we look at aviation sector and specifically in engines, because GE Aerospace focuses on the aircraft engines, there are different stages during which manufacture inspection happens, right? So just before I get into this, I'm actually going to focus my topic on the automation part, because you must be aware that that's one of the recent trends that's happening, right? Both in automation of the inspection itself as well as automation in the interpretation of the inspection. So that is the aspect that I want to focus on, and I'll cover that. So when it comes to inspection, inspection happens first during manufacture of a component or a part, and then the next is inspection during the service, right? And that inspection can happen in the case of an engine. Ideally, if you can do the inspection when the engine is on the wing itself, that's the best case because you don't have to dismantle it. But that's not possible because most of the components are difficult to access when it's on wing. So then it's the other option is when it's off wing. So a lot of the inspection that we do is actually off wing, particularly when it comes to eddy current inspection. And many different types of inspection methods that are used. Eddy current is just one of them. One of the applications that we are also very actively working on is to look at how we can replace fluorescent penetrant inspection with eddy current. Because if you think about it, fluorescent penetrant inspection is very widely used in the industry. It is a surface technique, lot of chemicals and processes involved in that. That is an area where you can actually replace that with eddy current. So that's a couple of applications that we are looking on into currently. I will come to that a little later. If we look at the different steps that are involved in the inspection, there is starting from the data collection to data interpretation, whether it is, and then classifying it as whether it's a pass, fail, or part that can be repaired, and then the documentation part of the inspection data. And in all of these, most of it is happening in a manual manner now. Some things are in a semi-automated fashion with a rig, and very rarely you see a fully automated inspection system. Any questions here? Okay. So when we talk about inspection automation, we have to look into various aspects. Starting from, we usually when we talk of an inspection, we talk of an entitlement of the inspection method. When we talk of the entitlement of the inspection method is in ideal conditions, if we were to do, let's say in the case of an eddy current inspection, you have a probe, you have a sample, a clean sample, you do an inspection in the lab, you will be able to inspect, let's say a 10 mil flaw or a 7 mil flaw. But then when it actually take it to a real situation, things change, right? So there are application specific factors, a lot of human factors that come into inspection. And human factors are one big variable in our inspection data. So if we break down that human factors thing itself, it goes into training experience, how the personality attitude of the person is, the cognitive skills, whether the person is stressed out, all of that. And then the nature of the task itself. I spoke about inspection of these components. Some of these components are difficult to access, or we want to inspect areas that are difficult to access, constrained area inspection. So that becomes an ergonomic problem for the inspectors, and then the associated complexity of the task, then the time pressures involved, right? And the work environment. All of these translate into the performance of the inspection. And generally, if it is a routine inspection that is done, the probability of a human error is like, let's say it's 1 in 10. If it involves thinking, in eddy current particularly, you have to look at the screen, look at the impedance plane data, interpret it, and then say pass fail. Sometimes it's simpler, just setting a threshold and just saying pass fail. But when there is thinking involved, there is more likelihood of a failure or a error happening. And then if you're also under stress, then the probability of an error is almost 50%. And then why are we talking about automation of inspection? In eddy current, again, even now, a lot of the inspection happens with single coil probes. And if you have to carry, if you have to do a large area coverage, then that takes a lot of time, right? So that's one aspect, then the human aspects in it as well. At a higher level, if you look at why you want to automate, we want to improve at an engine level, service provider level. You want to improve the turnaround time. Once the engine comes in to an MRO for maintenance, you want to inspect as quickly as possible, as reliably as possible, and then send it back so that the time on wing, TOW is the time on wing, can be increased. You want to minimize the time in the MRO shop. The other important aspect is the reliability and consistency of the data. Depending on how the setup is, who is doing the inspection, there are different MRO shops that are there across the world. Depending on who is doing the inspection, where it's happening, there can be a lot of differences that are there. Even within the same shop, depending on who the operator is, there can be differences in interpretation of data. So that's another aspect. Then there is, even the automation involves higher upfront investment, operational costs lower. Another very important part is the digital records for lifing. So typically now what happens is every time the engine comes in for inspection, there is a record that is made, but to have a connection of all of these records over the lifetime of the part, starting from manufacturing till its entire lifetime, maintaining part-wise records, that is a very key aspect of it that gets enabled through this automation. And if you look at the different steps that are involved in the inspection process, starting from the sample preparation to set up what kind of fixtures you're using, how do you actually deliver the probe? Is it a person moving the probe, or is it, you attach it to a fixture and then the fixture is on a robotic arm and then that moves the probe on the sample? How do you set up the instruments? And then the data acquisition itself while you're scanning, the interpretation of the data, and then the documentation of the data. Most of these steps can be automated, and what I'm talking about more here is on the last three parts about the data acquisition. Actually, we are also trying to do the automation of the data collection itself, which means that the probes are attached to some robotic arms, and then you move the probes with the robotic arm and then collect the data, and then you process the data. Any questions so far? Okay. So I do want to spend a little bit of time on the probability of detection. This is a very important aspect of when we talk about the capability of detection or a capability of inspection system, right? So usually when we want, particularly in aerospace industry, when you have an established process and you want to move from one process to another, so let's say moving from a manual process to a semi-automated process to an automated process, we want to make sure that we are at least as good as the previous standard, right? So we have data that has been collected in a consistent, in a study, like, in a particular application case, you can do probability of detection study, for example, to understand under various conditions, what is the probability of detecting an error with a certain confidence. So 90% probability of detection with 95% confidence intervals, right? So when you want to move to a new method or an automated method, you want to make sure that your probability of detection is as good or better than what you had before. You also want to make sure, because it's not enough that you detect a small flaw, but it's also important to ensure that you don't miss bigger flaws. So you want to make sure that the maximum flaw size that you miss in an automated inspection also does not exceed the number that manual inspection misses. Right? And typically, we do a confusion matrix to compare two processes and make sure that, the false positive rates are not too high with an automated system. because depending on when it's a manual person interpreting the results, sometimes the person can use additional tools and processes to come to a conclusion. Automated defect recognition, depending on the how smart the algorithms are, it may be limited. So we want to minimize the false positives, but at the same time, the primary requirement is that we have no false negatives. Right? So we do not want to miss anything, any indication at the same time. So that's actually a lot of times a difficult problem, because compromising, not wanting to have any false negatives, and at the same time minimizing false positives is often a big challenge in the algorithm development process itself. So when we want to do the probability of detection studies for this system, what we typically do is, there is the mill standard, and based on the mill standard, you want to make sure that you have enough number of sensors, enough number of samples. Typically what we do is like what is called a hit-miss POD. So which means that we are only interested in saying that am I detecting a fault or not, am I not detecting a fault. There is also another POD curve that you can generate, which is called as A hat versus A, which is size of the flaw on your x-axis versus the amplitude of the response of the flaw on your y-axis. You also want to make sure that you have enough surfaces without flaws to make sure that you can look at false positive rates and such. So we usually do these POD studies with the probes in a very realistic situation with all different variables over a range of sample sizes to determine the capability of the system. And then we want to make sure that when we do it on an actual system, we're able to see this, right? Because sometimes when in the actual system, there may be some variables that we haven't captured here. Although the intent of the POD study in reality is to make sure that you actually try and capture all of these effects as well. Please stop me if there are any questions. Any questions so far? Okay. Yeah, so in our application, the requirement that we have is to detect like a 15 mil indication, anything greater than 15 mil. So this POD study was to show that the A9095 is actually about 14 mils. Also, this is, we had very limited sample sizes in the low sample region, which is why you see the curve is not like a usual S curve, but that was what we had in the lower sample size region and therefore limited. So coming to some examples of the eddy current inspection automation that we are looking at, right? In some of the cases, so this is an example where a person is actually manually scanning the data with a probe on a part, and then there is a manual readout. And in this case, a threshold is set to a certain value. If the amplitude is greater than that value, then you reject the part. And one of the big problems with this, this kind of an approach that we have come across is that lot of times in parts that are critical to the engine, for example, where safety is a critical aspect, let's say you set your threshold as 3 millivolts or whatever, right? And then the operator sees that the value is 2.9 or 2.8, 2.7. It's close to 3, but it's less than 3. But a lot of times the operator wants to err on the side of safety, and therefore they would actually fail the part even though potentially it can pass, it is actually a pass. So typically when it's around very close to the threshold value, and similarly, there can be mistakes made as well, right? If it is above 3, let's say 3 set as threshold, it's 3.1, somebody accidentally makes a mistake. So a lot of the, we've actually done a study to see that the yield with an automated system can be significantly higher than with a manual system just from the operator interpretation of the result around the threshold. Also, currently in a lot of processes, the operator is actually looking at the screen and making manual records in a sheet of paper. Again, when you translate from the screen to the paper, there can be mistakes, right? So automation of this process, the manual scanning process, to with on a robotic arm to get a more consistent coverage, to get faster coverage, either with robotic arm crawlers, other delivery mechanisms. That's one aspect. You can do an automated calibration to do your gain and phase corrections, and then an automated defect detection. Right. So those are the different steps. So you can have these probes that are mounted on. This is a Fanuc robot, and we have a probe that's mounted on the at the tip of that. You can put your coordinates in for complicated scans, however you want to do it, and then scan the probe with respect to the part. And then you can, depending on what kind of probe you're using, you get raw data which has a lot of noise in it, a lot of false positives in it, and then you clean it up, process, and then show indications just which are above the threshold. This could also be a screen where you just show like a green and red if there is an indication above your threshold, right? And once you have this kind of a data in a digital format, then saving it becomes much simpler. You have a digital record of that. So instead of this manual data entry corresponding to the part, you can go to that. So that's one. And yeah. Somebody had a question? Okay. Yeah, so this is another case where we were actually, this is a case actually where we are actually trying to replace the current process is a fluorescent penetrant inspection on these dovetail sections of the blades. And fluorescent penetrant inspection actually requires, in this particular case at least, that there's a thermal etching is required to open up the indication so that when you apply the dye, it penetrates into the indications and you can actually see it. And this thermal etching process is quite expensive. So just eliminating the thermal etching process itself is a lot of cost savings, in addition to all of the associated FPI related costs, right? So, and with an eddy current system, what we have, what you see here is this kind of a blade. On this fixture, around this fixture, actually, we have a flexible eddy current array probe mounted. And with the robotic arm, you can kind of push the blade along this scanner, in this corridor. And as the blade gets scanned along the corridor, the entire dovetail on both the sides, the convex and the concave sides, get scanned. And the operator can look at the data, and then it shows images after doing the post-processing to show that on either the convex or concave sides, if there are any indications. So in this particular case, we've given 3 different levels. Black is like below the threshold. In some cases, the customer wants to, there is a hard threshold. If it is above a threshold, you fail it. But they also want to have a region where they mark and say that it is below the threshold, but it is in this region where it's just below the threshold. So you have the flexibility to introduce an additional level and then mark it appropriately. And then the operator just has to look at this screen instead of a screen like this, where they have to look at values and to see if it is above a certain value, then make this indication. You get, in this case that I was talking about, there is a case where we do manual inspection of these dovetails as well. And in that case, on a jig, you have a single coil eddy current probe that does just raster scan, right? Up and down you go. And then you cover the entire area. It takes time. Person is looking at the screen and making notes of whether there are indications or not. So this way, in one shot, you can cover the entire area. You can have an automated interpretation which is consistent. It's also important in these cases when you make it automated to have diagnostics built in. So that is another aspect of this. And just changing the fixturing, because we are using a flexible array probe. In this particular case, you can actually wrap it around different sections. So in this particular example, we have a a fixture that kind of wraps the probe along this curvature. If you have another part with a different type of curvature, you can wrap the probe around that curvature and then you scan. So you modify your fixtures, you attach those fixtures to the robotic arm, you do the scanning, automate the data acquisition, interpretation, and display, and then you can sort of have a much simpler and consistent system to give the inspection data. Any questions? Okay. Okay. Yeah. Okay. So, yeah, basically, if you look at while we doing this process, I talked about diagnostics. How do you know that the data is good, right? The data that you're collecting is good. So a lot of times what we do is, even though the one aspect is because you're doing a robotic arm to do the scanning, it's actually much faster. So you could do like 3 sets or 5 sets of data collection in much less the time that is being taken currently. And you can look for correlation between those data sets to make sure that the 3 sets or the 5 sets of data that you've collected have consistency between themselves. That's a first check, right? Sometimes we've seen cases where in 1 or 2 data sets you see some spikes, but you don't see it in the rest of the data sets. So if there is no consistency between the data sets, that raises a red flag. So, and there are cases where maybe there is some small dust particle or something that was lodged somewhere, the cleaning wasn't perfect. That gave a spike in one instance, but in the next instance, once a probe has moved over it, you don't see it anymore, right? So then you take 3 out of 5 or 4 out of 5 of your best results and so on. So having enough data sets to look at to make sure that your data is consistent and as expected, having the diagnostics built in is one thing, one important aspect. Also, in especially in the aerospace industry, it's not easy to change processes going from one to another. So usually the process is from manual to semi-automated, and even when you go to automated, there's a lot of validation that needs to be done. And in the validation studies, that is a good opportunity where you can actually evaluate your false positives and false negatives. And typically you start being conservative, setting your thresholds low enough so that you don't have any false negatives. You don't want to miss any false, which means that you end up with a lot of false positives to start with. And then you make your algorithms rugged. Particularly in the case of array probes, you have advantages to make use of the array configuration and the redundancy in the data, because you will have information that is being picked up by not just one coil, but you have adjacent coils in the same row as well as adjacent rows. So you have more information on a single floor, and you can use that to improve your algorithms and reduce your false positives. And also looking at ground truth, understanding the causes of that. In the case where you have FPI versus eddy current, for example, that I was talking about, when you do a validation study of an FPI versus eddy current, if you just compare with FPI, there are many instances where an eddy current signal will show that there is an indication, but FPI does not show an indication, right? In reality, most of those are not false positives in the true sense of the word, because the eddy current also picks up defects that are subsurface, whereas the FPI is not picking up those subsurface defects. So that is where some judgment has to be made. We'll have to actually cut up some sections to validate the ground truth and categorize them appropriately, and then And in a lot of cases, you'll have to use historical data on parts to understand that, okay, this is a reasonable threshold to keep, and these are false positives that you can deal with, sort of thing. In the case of automated inspection, another aspect is sometimes maybe there are things, a lot of times what happens is the automated algorithms, the automated approach actually catches indications that the operator may have missed. But it is possible that maybe there will be some things that a human operator would have caught. So if you look over a large enough data set, you will kind of cover these different scenarios and understand what happens. Again, as I mentioned, the investment cost can be high initially, but over time, the ROI comes up. The skill requirements are different as to the operator, from the operator point of view. Other things that come into picture are in terms of data security and getting the regulatory compliance approvals is a big aspect of moving to an automated inspection system in aerospace because of the processes that have been in place and having enough data to prove that the new method is good enough to move to an automated system. In spite of all of the challenges, it still has a lot of advantages, primarily from the point of the biggest thing is the interpretation, moving from subjective interpretation to an objective interpretation, reducing the need for qualified people, and also resource optimization, right? And as I mentioned earlier, it improves the efficiency in inspections, turnaround time decreases, and so the actual time, usable time improves. Consistency of the data, reducing human error, that's the first thing that I mentioned. And then it's scalable, right? And digital records, which are missing a lot of times in the current way of inspection. So that's a quick overview of what I had.
Are there any questions? If you have any specific questions, we can come and ask here, I think. Yeah. Wait.
Okay. Sure, most welcome. Yeah, thank you. Thank you all.
Yeah. So let me introduce Dr. Arasu. He'll be talking on applications of eddy current testing, tube inspection, and some advances. Dr. Arasu is currently heading electromagnetic measurements and structural integrity section of ND division in metallurgy and materials group at IGCAR. He obtained MSc in physics from Madurai Kamaraj University, Tamil Nadu, and PhD in engineering sciences from Homi Bhabha National Institute, Mumbai. His research interests include numerical modeling of electromagnetic ND, image processing, and developments of novel electromagnetic ND sensors and systems. He has over 50 publications in peer-reviewed journals to his credit. He is a recipient of National NDT Award for NDT Systems and Innovations and Development in the year 2015 and DAE, Department of Atomic Energy Group Achievement Award in the year 2016. So let us hear from him. So please, Dr. Arasu, over to you.
Thank you, Mr. Kale, for a kind introduction. Am I audible? Okay. So my main agenda of this talk is tube inspection and some advances I would like to cover, especially remote field eddy current technique and sweep frequency technique, and some role of artificial intelligence in eddy current testing. A few slides I will show. Okay, and in addition to that, I have another this thing also that I will quickly recap certain concepts that previous speakers covered, which will be useful for you to recall. Okay, go to the next slide. Hello. Next slide. Go next. Okay, this slide actually will be useful for you. Actually, I will share this slide with you. Actually, it gives you the sequence of eddy current testing. What is happening when you are doing eddy current testing? We are using a simple coil as a sensor, is the first one. And the second one is across the coil, we apply a sinusoidal excitation, time varying current, okay? And that will produce magnetic field around the coil. That magnetic field also will be oscillating, okay, because it is a sinusoidal excitation. So when that setup is kept on a material, that is the fifth one, eddy currents are induced in the materials according to the Faraday laws of electromagnetic induction. Okay, that eddy currents also will in turn have a secondary magnetic field. According to Lenz's law, the secondary magnetic field will oppose the primary field. So there is a net change in the magnetic field which results in the change in the applied voltage of the coil. Okay, so that is what is being detected as our Nageshwar Rao has told, that small change in the voltage only is being detected with the use of a sophisticated instrumentation. Okay, this is the eddy current testing in nutshell. Okay, go to the next. And there is a small animation which to fix up your ideas. There is a coil, there is a excitation, current is going, there is a magnetic field setup, and it is also oscillating. When it is kept in a material, eddy currents are induced, secondary fields are white in color. When there is this setup is on a material with a defect, okay, eddy currents are going in a different path. So secondary field changes, so net field is also changing, and then voltage is changing. Okay, so I think this will make your understanding more clear and firm. Okay, go to the next slide. Next slide. So skin depth is the most important phenomena that every speaker has covered. What I'll do is I'll do an illustration. Next. I have in this particular table what I have given is I have given certain materials in the increasing order of resistivity I have given, and I have calculated the skin depth at 100 kilohertz. What would be the skin depth in those materials, and what would be the skin frequency to achieve 1.5 mm skin depth in this material? That is the inverse problem of that. Okay. So usually I have given something like what is the resistivity. Okay. We express resistivity in terms of in units called micro ohm centimeter. That is because when you express resistivity in micro ohm centimeter, we don't have to use any exponents like 10 to the power of minus 6, minus 7, something like that. So it can be something like a whole number with some decimal points. So what you can see is aluminum is having least resistivity and so on. Highest resistivity is Inconel 600 in the materials that we have chosen. So from resistivity you can calculate what is conductivity. Conductivity is basically reciprocal of resistivity, 1 by of rho, okay? So we use some unit called percentage ISES, that is percentage of International Annealed Copper Standard. That unit is basically what we are doing in this is that the copper's conductivity is taken as 100%. So all the materials conductivity is compared with respect to that. So that is what is percentage ISES. So you can see conductivity is decreasing as resistivity is increasing, conductivity is decreasing. So for example, aluminum is having 64% conductivity, highest conductivity among these 5 materials. Okay, so what would be the skin depth? That is, skin depth means standard depth of penetration in that material, where eddy current density falls to 1 over E, that is 37%. Okay, so you can use that formula, whatever is given, that 50 under square root rho by mu or F. Okay, usually whatever earlier speakers have told is that delta is 1 by pi f mu sigma. So in this formula, you have to feed the frequency in hertz. Permeability is permeability of the material, that is permeability of the free space into relative permeability. And sigma is the electrical conductivity of the material, that has to be fed in SI units. But we have given one formula, that SDB formula. In that you give a frequency in hertz and permeability in relative permeability units itself, that is the dimensionless number. And instead of conductivity, you can give rho in micro ohm centimeters. Okay, so you can see that as conductivity decreases, eddy current depth of penetration is increasing. For example, in inconel material at 100 kilohertz, you are able to penetrate a depth of 1.5 mm, whereas at same frequency in aluminum you are able to go only 0.2 mm, 0.26 mm. So you can see the vast difference of standard depth of penetration at a given frequency. So I have also given for 1.5 mm skin depth what would be the frequency. If you look at that, for aluminum you have to go very low frequency. So that is what all the speakers have told. So in a nutshell, this table gives you enough feeling that what is skin depth essentially. Okay, so you can see that there could be some 5 questions in each column. Okay, there are 15 questions which can be asked from this table. So this table is rich in information. Next, I will skip that because it is already talked about. Skip next. About probes, classification of probes, I would like to reiterate once again that Mr. Arvind Kumar has very clearly covered it, but still, based on the operation of the probe, we classify probes into 3 categories, that is absolute, differential, send receive. Okay, absolute probe is you apply excitation in the coil and look at the impedance of the same coil. Okay, differential is basically there are 2 coils which are oppositely wound. The current is opposite to each other. In one coil if it is counterclockwise, in the other coil it is counterclockwise. So that the difference in impedance at a given instance is looked at, that will be 0 for any good condition. Okay, and both coils impedance changes are measured in this. Okay, the cumulative means the effective impedance change is measured. On the other hand, in TR probes, that is transmit receive probes, one coil is transmitted. It will produce only eddy currents in the material. Okay, and there will be a reverse receiver which will not be excited with any current or anything, but it will be sensitive to the eddy currents which are produced in the material, and it will pick up that, and the voltage corresponding to that is measured. Okay, this TR probes have certain advantages as compared to absolute and differential probes. I have also given where these probes can be used. Okay, for example, absolute probe is good for measuring thickness, conductivity. Differential probe is very good for detecting localized, highly localized small defects, and it is insensitive to certain gradually varying geometry or temperature or whatever. And for send receive probes are mainly used for oriented cracks. I will come into the details of it in a few slides. Okay. Next, please. So based on the geometry that we are going to inspect, probes are again classified into 3 categories. That is surface probes, mainly used for plate components, and bobbin probes, which are used for tubes, encircling probes, which are used for thin, small diameter tubes and rods, wherein you encircle the material, okay? The probe is outside, wherein the bobbin probe, the probe is inside, okay? Clear? So we can have a surface absolute probe, surface differential probe, surface transmit receive probes. Similarly, we can have bobbin absolute differential transmit probe, transmit receive, okay? Similarly in encircling also. So these are the major classifications of probe, but there are certain hybrid probes are also possible. For example, there is a single exciter and a differential receiver coil probes, something like that. Okay. Next, please. Next. So when come to tube inspection, you can say that when you use an absolute probe, we get only single lobes. That is one simple change in impedance and then going and coming back. Okay, kind of signal. But when we are using a differential probe, we get 8 pattern kind of signal. What we call it as Risajos patterns. Okay. It has some significance because it basically looks at the two sine waves which are interacting at different phase angles. Okay, in the probe, in the differential probe. Okay. Next. So let us come back to the NDT of tubes. In the tubes are majorly classified into, I have classified into magnetic, non-magnetic. Eddy current testing means it is non-magnetic tubes only so far. Okay. So non-magnetic tubes, we have several applications. We can do quality control inspection, quality assurance of the tubes during fabrication, and we can do eddy current based inspection during in-service. Okay. So ISI, in-service inspection. In both these conventional eddy currents are used. Most of the times for QA, fabrication related inspection, we use an encircling differential coil. That is because automation is very easy. Whereas if you use a bobbin differential probe, it will be slightly difficult. You have to push and pull the tube, pull the probe inside the tube. Okay. And most of the times when we are carrying out inspection at the shop floor, ODA of the tubes are accessible. Okay, so it is better you use an encircling coil. So I will cover the ISI part in a more detailed manner. When it comes to magnetic tubes, we have certain issues of applying eddy current technique. There are 2 issues which I will again discuss in detail in the coming slides. For quality assurance and during fabrication, we use what is called a saturation eddy current technique, which will be avoiding certain limitations of the eddy current technique to detect defects in shop floor conditions. Whereas for installed components where OD is not accessible, we cannot use eddy current technique. We have to go for something called a remote field eddy current technique. I will have a couple of slides on remote field eddy current technique also. In remote field eddy current technique, we have a single exciter. We can have one single receiver or dual differential receiver and so on. So this slide basically gives you in nutshell the NDT of tubes, okay, ECT of tubes. Next, please. So I'll cover, as I said, I'll cover the ISI part in more detail because encircling based differential inspection is a standard inspection. There is no challenge in it. Whereas in ISI, we have certain issues that I will come back. Okay. As you know, the major applications of eddy current technique is inspection of heat exchanger tubes. Heat exchangers are workhorses of power plants, like nuclear power plants or any coal-fired power plants. And eddy current is extensively used for detecting many different types of defects. Next, please. Next. Okay. So in this slide, actually, this is a very famous slide. It is shared by everybody. I will also share with you. What are the types of defects that we will look for when we do eddy current inspection of heat exchanger tubes? I think you can read it, it's self-explanatory. Like say for example, what are the possible defects that can be introduced during the fabrication stage, which can be detected during ISI, and what are the possible defects which would be introduced in the material when it undergoes operation, means when it is under operation. Something like intergranular stress corrosion cracking, denting, conductive deposits which are causing trouble, tube to tube wear, things like that. Okay, there are something called freeze bulge in condenser kind of applications where and fatigue cracks. So there are many different type of defects that are possible during heat exchanger operation, which can be detected by eddy current technique. Next please. And whenever eddy current testing is done for in-service inspection of heat exchanger tubes, we follow this code, that is ASME section 5, article 8, which gives you in-service inspection of eddy current inspection of non-magnetic heat exchanger tubes. That is the title of the standard. And it provides a calibration standard which consists of a through hole, 80%, 60%, and 40%, and 20% flat bottom holes. Percentage means percentage of wall thickness. 80% of wall thickness, flat bottom hole of some particular diameter. That varies from tube diameter to different tube diameters. Okay, and most of the times, no, these heat exchangers are supported by what are called support plates or baffle plates. So they cause a lot of trouble during inspection. So we use something called multi-frequency testing. I will deal it in very detail in the coming slides. So we use multi-frequency testing for eliminating the signals due to support plate and bring out defects which are present under the support plate. Next please. So some little bit of motivation I will give you. Like if there is a tube and there is a bobbin differential probe when you are doing ISI, you just scan it, click, excuse me, it's a click, 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 click. So when you are just scanning, you don't get any signal because there is no defect. You get a zero output in the impedance plane. Okay. Next. Click, click. So when there is a defect, you get an 8 pattern. Okay. We get a clear signal. This is called a Lissauge's pattern. Next. When there is a support plate, that time also when you scan, we get an 8 pattern, again like a signal. So this is not due to defect, but it is due to a geometry which is unwanted for us. So we call it as a disturbing noise. Okay. So such a disturbing noise has to be eliminated. Why it should be eliminated? Because next. When there is a defect which is under the support, so how can we detect? Click. So it essentially gives you some signal in the impedance plane, which is a composite of a defect as well as a support plate. So we need to eliminate the support plate's influence and take only the defect signature so that we can reliably say that there is a defect under the support plate. So for this case only we use the multi-frequency mixing algorithm, what is called a mixing algorithm. A little more details of the multi-frequency mixing I will discuss in the next slide. In this, what we normally do is, we use two frequency excitation. In the first frequency is basically the SDP frequency, which is calculated based on the skin depth formula. And the second frequency is usually a lower frequency, which will be more sensitive to support plates than surface defects. Okay, in this case, what we normally do is, the second signal due to the disturbing noise alone that we will take, and then we will do some operations on that, so that the first frequency 1 signal and the second transformed signal will be looking like the same. Are you getting the point? If any doubt, you just disturb me, means you can hold me for some. What you do is, two frequencies, we take only the support plate information in both the frequencies. The second frequency signal alone, we do some operation so that it looks exactly similar to the first frequency signal. In this condition, we do a algebraic difference, that is called mixing. Okay. So for if you do an algebraic difference of these two signals, the F1 signal and the transformed F2 signal, what we normally get is a 0, right? So your support plate is eliminated in the mixed channel. Is it clear to you? Any doubts? But this process, if you adopt for defects, it will not be same, okay? Because defects are usually in a different phase angle, different amplitudes, and so on. So it is only applicable for the disturbing noise that you have considered to be eliminated, okay? Clear to you? Don't follow all these things. They are just some details of it. Somebody who is interested in, they can read it and then try to understand. So what normally we do, the transformation is that we rotate the signal, we scale the signal in both the directions, horizontal and vertical directions, so that it will look same as that of the F1 signal, okay? So that transformation is essentially represented as a matrix. That's what I have given here, okay? So the method is clear, right? You take the disturbing noise, you do some operation and do a mixing operation, so that you get a zero output, only for the disturbing noise. Next, please. So in this, I have given the clear, means the signals, impedance plane signals of all the disturbing noise in both the frequencies, transformed one and then mixed one. You can see that F1 signal is the blue color one, and F2 signal is the red color one. I have considered only the red colored one made into look like the blue color one, okay? Did something on that so that it is exactly matching with the blue color one. And now I take the difference, that is what is the black in color. So some residue is also there because my mixing is not exactly, it will not be exact, okay? It will not be exact. Whatever operation we do, however perfectly we do, there will be some residue, okay? So this is what is mixing is all about, and I will give you some outputs. Next, please. So the signal, whatever is shown on the top left, is that a through hole is under the support plate, okay, for which the composite signal is given like that, F1 and F2, whereas the mixed signal is free from the support signature. You are able to see that, right? Clear? So we, in the process, we have eliminated the signal due to the support, that is the disturbing noise, and then brought out the signal due to the defect alone. I hope I am getting across to you, okay? So similarly, there is an 80% flat bottom hole which is under the support plate. The F1 and F2 signals are shown, and the mixed signals is also shown. So you can see the mixed signal is very clearly a 8 pattern, which is characteristic of a defect. Next, please. So this is the this thing of this. So the question comes that whether we can mix more than one disturbing noise in a given inspection condition. The answer is yes, true. We can mix many sequences. For example, we have an issue with the support plate, and there are a lot of denting in the tube. So we have to remove the denting, which is another disturbing noise. Support plate is the already existing disturbing noise. So what we can do is we use two frequencies. First, to remove the support plate information, and we derive a mixed channel, and that mixed channel, and use another frequency in which you take only the denting signal as the disturbing noise, and this denting signal as the disturbing noise in this mixed channel also you take. Do another mixed channel, okay? Do another mix to get only the defect information. Clear? So you can do this process as many times as possible, but there are problems, right? So the first mix is to eliminate support, the second mix is to eliminate denting, okay? And the resulting signal due to defect, okay? The golden rule is that if you want to suppress n number of disturbing noise, you have to use n plus 1 mixing frequencies, okay? N plus 1 mixed frequencies. So can we do it, whether n can go to infinity? No, it cannot go more than 3, because for every mixed process, we get a lot of residue. So that residue will essentially increase the signal to noise ratio, okay? So decrease the signal to noise ratio, so that multiple mixes will result in a lot of noisy data than the signal data. So more than 3 mix is very difficult to achieve. Next, please. Any doubts so far? So I have covered a tube inspection. In a nutshell, I have given what are the techniques which are used and what is the typical problem of heat exchanger tube inspection, how multi-frequency technique is possible to eliminate disturbing noise. Okay. Now we will come to some of the limitations of differential encircling or bobbin type probes. Is that defects which are oriented along the circumferential direction, because your eddy currents, no, eddy currents in the tube or bars or thin wall tubes, no, it will be like in the circumferential direction. It will be same as like concentric rings in the tube. Okay. So if a defect is oriented unfavorably, that is, it is not disturbing the flow of eddy currents, which will give very less sensitivity to detect. Okay. So defects oriented in the circumferential direction sometimes get missed. They have very less sensitivity, and most of the times it gets missed. That is one major problem with this encircling or bobbin type differential coils, which are routinely used in our inspection. That is the only major problem. The other problem is that it is not a problem with respect to inspection of detecting defects, but with respect to localizing the defects. For example, in a tube, the circumferential cross section is shown. We have one single defect at 3 different locations. Okay, all will give you the same signals. So you may not be able to say the defect is there in the 1 o'clock position or 8 o'clock position or 12 o'clock position. That you cannot say. So we have to improve the localization capability as well as sensitivity for defects which are unfavorably oriented to eddy currents. Okay. So to avoid this limitation, certain developments have taken place. What are the possible options are that one is you can have a small pancake kind of probe and you can rotate inside the tube. So that is possible. And you can also use a surface probe in TR mode, which will be sensitive to directional flaws. Okay, that I will illustrate as I was telling now. Okay, so these are the possible options. I will go one by one. Next, please. So first comes is that motorized rotating probe. So there is a thin, small coil, and in this case, especially that this is called a plus point coil. That is, if you look at from top of these are orthogonal coils, which are small coils which are orthogonally assembled, like what I have shown in the picture. And each coil will have its orientation. Means the eddy current orientation for the first coil is, let us say, in this direction. For the second coil will be a perpendicular direction, right? Because the probes are perpendicular to each other. So any cracks which are oriented in different directions will be picked up either one or the other. Okay. So this kind of MRPCs, motorized rotating probes, were extensively used for heat exchanger inspection in sometime before, like some 20-30 years before. So you can rotate this probe inside the tube helically so that it gets inspected. Okay, the full data you get. Next, please. So this MRPC data, whatever I am showing, is taken from literature, which are typically the nuclear power plant industry data. You can see that this is the raw data, which is because it is rotated inside the tube, the entire circumference is covered, and you can represent this as an image. So that is an advantage also. So the image at the extreme left is the raw image. We do some kind of filtering and all, so that defects can be detected with much confidence. So the zoomed in image is shown with a lot of defects. Okay, some defects are there here and there. Okay. So the main problem with this MRPC is that you are rotating the probe inside the tube. So for every circumferential position you have to rotate, it will take some inspection time. Okay. Whereas your bobbin type probe, you just simply pull. Okay. So the inspection time is increased manifold. So especially this is not good in nuclear power plants. So because radiation hazard is there. So persons cannot work for longer time in nuclear power plants. So that is a major problem. So MRPCs were not preferred at that time. So they wanted to change the MRPCs to some other new probes. So the alternatives were transmit receive probes. Next, please. So in transmit receive probes, as I said, there is one transmitter which will produce eddy currents in the material, like what I have shown here. There will be circular eddy currents in the component that is being inspected. And there will be a receiver which is kept slightly away, some 1 or 2 mm away. You can see a defect which is oriented in between the transmitter and receiver will offer very less resistance to the eddy current flow. Whereas you see in the other scenario, if the defect is oriented along the transmit receiver coil, it will offer large resistance. For example, I'll tell you, there are 3 eddy current lines. So only one eddy current line is disturbed in this case, whereas all the 3 eddy current lines are disturbed in the other case. So which will have more sensitivity? Definitely the other will have more sensitivity, right? So if we want to detect this TR probe, want to detect this probe, this defect, we can just rotate the probe 90 degree and still we can detect, right? Because the defect will be favorably oriented to eddy current perturbation. Clear? So using transmit receive probes oriented in different directions, you can detect all defects which are oriented in different angles, for example, okay? So next please. But this probes, actually this is a kind of calibration standard. You can, they have used transmit receive probes to make an image of the plate, okay? So you can concentrate on the L type defect and the plus type defect. You can see that when you scanned the probe along this direction, in the first one, whatever you have been shown, your L in the horizontal direction and the plus in the horizontal direction are detected very clearly. Whereas the other perpendicular one is not detected. If you change the direction of the scanning, means the direction of the probe, that is rotated the probe 90 degree, both the other arms of the defect has been detected. So this is the demonstration of the capability of transmit receive probe. Clear to you? Any doubts, please? So how these transmit receive probes can be used fruitfully for tube inspection is that they can be made into an array of probes like what I have shown. Next please. It is something like this. In this case, what you are able to see is there are 2 rings of coils which are, each ring has multiple number of coils, something like this, okay, which are arranged in a circumferential fashion, okay. So we can excite one probe at a time, like T1 for example. The other row can receive two sensors can receive R1 and R2. It can be either 2 or 3 or it can be only 1 also. And in addition to that, for the same excitation, horizontally the same row, adjacent coil can also see R3, okay. So that defect oriented in different directions can be detected. And this, you can click. So this excitation sequence will move from one probe to other. First we excite with one probe, take 3 different outputs, 3 different receiver outputs, switch the excitation sequence to the nearest probe and take again 3 and so on. It will repeat. So it will repeat till all the probes in the one row of the one row of the probe is excited. Okay. So this is the probe which was invented basically by this is G-Tech. Okay. Earlier there was a G-Tech company. Now many other companies have taken over from G-Tech and they are also selling the same type of probes. It's a patented technology. It's called X-probe technology. Clear? So you can get an image still. For every excitation, we get 3 channels output. Okay. 2 channels are sensitive to cracks oriented in axial direction, and the R3 channel is basically sensitive to cracks oriented in circumferential direction. So any defects which are oriented in different directions will be picked up by both the probes, both the excitations. Okay. Sorry, both the receiving sequence. Are you able to get the point? Is it okay getting across to you? Next, please. Next, please. Next slide. Okay, so essentially you get an image like what you have got in the MRPC probes. Okay, the complete image of the inner surface of the tube, which is inspected. So there are wonderful scope for doing a lot of image processing based algorithms, automated defect detection, whatever you can apply in ADS like automated defect recognition systems. Those things can be still applied for eddy current also. Next please. So this is the state of the art probes which are available in the market as of now, and we have done some developments for array probe. It is an encircling 4 element array probe. So 4 probes are there. Each probe is a surface differential probe. You can use it in absolute mode as well as transmit receive mode, and you can get multiple channel data. Okay. So these 4 probes are used for testing some small diameter tubes. The diameter of the tube itself is 5.1 mm. The overall OD itself is 5.1 mm, and the thickness of the tube is around 0.3 mm. Okay. So we are able to develop an array probe similar to the one that is there in the market, and we have used it for our application, one of our applications. Okay, so there are, as I said, there are around 10 channels of data we can take from this data, from this probe. Okay, this is used for what is called a fuel pin in nuclear reactors. Next, please. We have characterized this probe on standard defects. For example, we had a different type of notches, both axially and circumferentially oriented, as well as some through holes of different diameter. You can see the image of, you concentrated only one image. Okay, why the fourth image is there, I will tell you. One image is basically due to one coil. Okay, the topmost one is due to coil number 1. The second is coil number 2, coil number 3, coil number 4, and so on. So what we have done is, in order to characterize defect, characterize the performance of the probe. That is, we are orienting probes in 90 degrees. Okay, so in between 90 degree, if there is a defect, whether they are getting detected or missed, to assess that situation, what we have done is, we have taken the composite image of these 4 together, and we can see that all are giving uniform this thing, so that it essentially says that the probe will not miss any defects which are available between the probes, the individual elements of the probe. Next, please. So this is about non-magnetic tubes, the developments. So let us move on to magnetic tubes. So is it okay? We can stop and then have some discussion if you want. If there are any questions, pressing questions to you on non-magnetic tube inspection using ECT, we can stop and then go ahead. Okay? We have plenty of time for discussion. Any questions, please? You can also ask any questions based on the previous lectures, which can be answered. If you don't understand certain things in my lecture or as well as previous lecture, I can clarify. We can have some discussion now. Please. Before I move on to the non-magnetic tubes, yes, please come. First of all, it is clear whether whatever I have covered is clear. Okay. No, there are some more things. Some more. Okay. Yeah, I don't think so. No. Yeah. Okay. Okay. When it comes to magnetic tubes, there are 2 problems which are basically limiting the application of eddy current technique. The first problem is this, that is noise due to minor hysteresis loop. So essentially what we are doing here is that we are applying a sinusoidal excitation. So that means the magnetic field is varying. So when the varying magnetic field is kept on a magnetic material, over one cycle of the sine wave, we will come across what is called a minor hysteresis loop. You know what is hysteresis? If you ramp the voltage in a coil and then keep it on a magnetic material, first it will try to magnetize and then reverse the magnetization, but it will not follow the same path. Okay? So it will follow a different path. That is called hysteresis. Non-retraceability of the path when during magnetization as well as demagnetization. So essentially when you are applying a sine wave, that is what is happening. So across the minor hysteresis loop, your permeability is not constant. So it is keep on varying. Every cycle it is varying. And it also matters that in a magnetic tube, the magnetic domains of the material are randomly aligned, randomly oriented. So place to place, the permeability, the magnetic history is not same. So these are the two major problems which limits the application of eddy current technique for this. So finally, what will if you are just trying to measure by eddy current technique, you will get only a noise like this, the data which is shown here. Okay. If we can get rid of this noise, I will show you there will be beautiful signals under this noise. Okay. The second problem is skin depth equation. Permeability is in the denominator. When you are increased the permeability, what happens? Depth of penetration decreases. Okay. So I have given some data, like I have taken mu or 100 for a given non-magnetic and magnetic material. I have compared delta is 10 times less. For example, in a non-magnetic material, let us say 1 mm of thickness, your depth of penetration is 1 mm, let us say, at a specified frequency. At the same frequency, in a magnetic material with permeability 100 will have 10 times less, that is 0.1 mm only it will penetrate. Okay. So we cannot do volumetric inspection of the tubes. It is very difficult. Okay. But one thing you can do, you can decrease the frequency so that skin depth increases. So how much you can decrease the frequency? You can 100 times you have to decrease the frequency. Okay, suppose 100 kilohertz is the optimum frequency for a non-magnetic tube. Same for a magnetic tube of mu or 100, it will be 1 kilohertz. So at 1 kilohertz, your sensitivity will be very, very low. It will not detect small defects. Okay. It will detect very large defects, which are, again we have this problem, this hysteresis problem, which will again introduce some more noise into it. So magnetic tubes not possible to be inspected by eddy current technique. What are the solutions? Next please. So one solution is that you magnetize the tube, okay, saturate the tube with magnetization, that is high magnetic field you apply, DC magnetic field, and in the same condition you apply eddy current technique. So what happens is your hysteresis variations are minimal, permeability variations will not be there. The delta mu changes are almost 0. So in that condition, if you carry out eddy current testing under saturated condition, you can get very beautiful signals. There are two through holes which are seen. One component only I have shown, just to appreciate that how much of SNR improvement is there by magnetization. You can see that 23 dB means completely the signals are submerged in noise. We are not able to detect anything. But when you magnetize and do the same thing by eddy current, you are bringing out the defect signals. Right? So saturation is one point, one method by which you can do eddy current inspection, but still there will be, with respect to skin depth equation, some problems will be there still. Okay. Clear to you? So for production cases, if your magnetic tubes are there during fabrication, you magnetize the tube and do eddy current testing, which is called saturation eddy current testing. Okay. So problem solved in production stage. But in service inspection, we cannot magnetize a component. When, for example, when there is a magnetic heat exchanger, you cannot magnetize tubes because they will not be accessible. Second, the problem is there will be huge magnetic field is required to completely magnetize the tubes. That is not possible. So what other alternatives? There is a technique called remote field eddy current technique. I will come back. Next please. So I have given some field lines, all those things, but let us not bother about that. Essentially, there is an exciter, there is a receiver, which is kept at a particular distance. Okay. Some distance which is far away from the exciter, something like 3 to 4 times the ID of the tube. Okay. What happens? The eddy currents due to the excitation coil will couple through the tube wall and then interact with the receiver coil, which is shown in green color. Okay, at some particular distance very effectively. So that is called a remote field. Okay, so that field is sensitive to the indirect field due to eddy currents, and eddy currents will carry the entire tube wall information. So if there are any defects in the tube wall, it will be detected very easily. Okay, so this technique is used very extensively for oil well casings. Like for example, a lot of oil well casings are made of carbon steel tubes. Okay, they are large diameter, thick carbon steel tubes. Either magnetic flux linkage technique has to be used or remote field eddy current technique has to be used. If you want to use the MFL technique, you have to again magnetize, demagnetize the tubes. But remote field eddy current technique, it is a low frequency send receive type eddy current technique which doesn't require any magnetization at all. Why it doesn't magnetization is required? It is over a larger distance of the tube, it is averaging out the permeability variations, and it is as well as a low frequency technique. Okay, so all your limitations are covered. Okay? So what is reported in the literature is that for a given frequency, if you do a conventional eddy current technique and remote field eddy current technique for a magnetic tube, you get a 3 times better sensitivity as compared to conventional eddy current technique. Okay, next. So we have modeled this phenomena. Essentially, it was a PhD work of mine. I have done some numerical modeling using finite element methods so that we can see the magnetic field profile inside the tube and on the tube wall, all those things. So you can see very clearly there are different zones like direct field, transition, remote field zone. Actually, the idea is that I said that there is an exciter coil and there is a receiver coil. You have to keep the receiver coil at some particular distance. So what is the distance at which you have to keep your receiver coil is the major question that you have to answer there. Okay. So we have to find out that. So what we can do is like, you can go to the next slide. Next slide, please. So what you can do is that you can do an experiment something like this. A stationary exciter, receiver coil is translated as a function of distance between the exciter and the receiver coil. And look at the induced voltage in the receiver coil. So what happens in the direct field zone, it exponentially decays. Y-axis is logarithmic. So after some particular distance, it again increases, which is essentially due to the indirect field, that is field due to eddy currents. Okay. So ideally, we have to keep your receiver coil in this case, for example, between 30 to 40 mm. Okay. So we did this experiment for one of our applications, where we use what is called 9 chrome 1 moly magnetic tubes, steam generator tubes in our nuclear power plants. So in that we have applied this kind of technique. We did some modeling, we did some pull-out tests, all those things, find out what is the distance at which we can keep the coil and at what frequencies they are better detected, defects are detected in a better manner. Next, please. So these are actual pull-out test variations. So no, sorry, I'm sorry. This is a model-based studies which are done at different frequencies. What we have observed is that at 30 to 37 mm, there is a remote field characteristics exist, as well as in the frequency range of 100 to 1100 hertz. It's very low frequency, but still this is the technique which can be used for those kind of tubes. Next, please. So after the studies that we have carried out on the remote field characteristics, understanding what is the distance, what is the frequency, all those things, we have fabricated different types of probes which are useful for our steam generator inspection. You can see this is the probe head with an exciter and receiver coil which are separated by 35 mm distance, and with the 30 meter cable, the conduit which will be pushed inside the SG tube, and it will be pulled and then data will be acquired in that. Inspection will be carried out. Okay, next please. So in addition to characterization of the remote field eddy current technique, we have also carried out some amount of instrumentation to develop an instrument on our own for remote field eddy current technique. So we went for something like a modular approach, and we essentially look at the phase lag of the sine wave which is excited in the receiver coil. Okay. So we did some sophisticated instrumentation. Based on that, we could detect some defects. You can see there is a tube in which there are some defects are there. Okay. Okay, next, please. So these are a variety of defects which are present in this 9 chrome 1 moly tube, which are detected by our probe, and their signal to noise ratio is very good, and we are able to detect positively by any wall thinning variations of up to 10% of wall thickness. Okay. Next, please. So what I was telling is that there is a single exciter and there is a receiver which is kept at the remote field zone. But what will happen if we replace this single exciter, single receiver, with a multiple receiver coils? Okay, so we can take image of the tube, okay, like what I have shown in the array probe or the MRPC probes. So we have developed something like this. We have stacked coils in a staggered manner so that we can put as many coils as possible. So 8 coils we have put in this case. And this is the probe, okay. At a time it will acquire only one data from one of the receiver coil. And there is a single exciter which will excite sine wave in the tube, eddy currents in the tube. Next, please. So again we characterize the probe in the same way like what I have shown in the array probe cases. Next, please. And these are the images of defect, a variety of defects which are obtained by this remote field eddy current array probe that we have developed. Clear, huh? Good. I think for the non-magnetic case, one is saturation eddy current technique, which can be used for quality control during fabrication, and which cannot be applied in in-service conditions, for which 9x1 this RFT technique only is possible. So for RFT development for one particular SG tube we have shown, and we have shown like it is like eddy current, right? We are able to detect image, many things, right? Okay. So that covers non-magnetic tubes also. Any doubts on this? So what I have covered basically non-magnetic tubes for which eddy current technique is used, and bobbin differential based eddy current technique which was used for heat exchanger tubes, non-magnetic heat exchanger tubes, and multi-frequency testing, in that case how we can eliminate disturbing noise. Then some developments like array probes, TR based array probes, GTEx X probe, those technologies we have seen. And then in the case of magnetic tubes, I have demonstrated how this saturation eddy current technique can be used, and RFT can be used for ISI. Okay. Next, please. So this is again the essence of what I have started with and I have completed. Okay. So at this point also we can have some questions if you want. Any questions? At least in this table, any problems are there? If you want to do tube inspection, it will be very helpful for you, right? Next, please. So next. So I'll touch upon a little bit on the sweep frequency eddy current technique. Okay. So in all the eddy current technique, we are using continuous excitation. We are using a sine wave of particular frequency, only one frequency. As a function of time, it is continuously varying. The voltage is continuously varying. So only one frequency at a time is used. Okay. Whereas in the sweep frequency, what we normally do is we take one frequency, excite the probe for one particular window, particular time, for a particular time, and take one impedance data from that, and change the frequency for the same time duration, take another impedance point, and so on. We change the frequency continuously, frame by frame. Okay. Say for example, I have given like this. 500 Hz is used for some 0.05 seconds, I think 0.05 seconds. Okay. And 1000 Hz is used for another duration, same duration, and 1500 and so on. Okay. So we can sweep frequency in particular range in a particular step. For example, you can 500, 510, 520 and so on also we can go. Okay. So what is the advantage of that? Next, please. This is sweep frequency. How does it work? Like, see, if you look at the inductive reactance component of a probe, XL, which is nothing but the 2 pi FL, right? 2 pi F is the frequency, L is the inductance of the coil. So XL goes to 0 when F is 0, obvious, right? When F is 0, XL is 0. When F goes to infinity, very, very high frequency, that time also it should go to 0. Why? Because of skin depth. As you go to higher frequencies, what happens is your depth of penetration is decreasing. Okay, so in a smaller volume, you have very high density of currents, high current density. Okay, so which will offer higher resistance to your applied voltage. So the voltage will become minimal and so on. So to two extreme conditions like at f is equal to 0 and f is equal to infinity, you get 0 output for the XL component. I'm just taking one XL component as this resistance component also, similar behavior will be there. Okay. So that means at some intermediate frequencies, it has to go to some peak and then come back, right? At one of the frequency, it has to go to the peak, right? So that peak frequency, we call it as peak frequency, FP. That FP is most probably corresponding to the standard depth frequency, delta, okay? So if you vary the frequency for any particular thickness of the material, you are bound to get a peak at one particular frequency. So how this is applied for thickness determination, I will show you next please. So I have in this case, this is a model data, but experimental data also will be almost similar to this. In this case, what I have given is frequencies varied from 1000 Hertz to 4000 Hertz in steps of something like 5 to 10 Hertz. Okay, frequencies varied, and then XL inductive component is seen. Inductive component is seen for different thickness tubes of whatever I have talked about, no, the 9 chrome 1 moly tube, which are steam generator tubes for us, right? So if you plot 1 by square root of the FP, that peak frequency you find for every thickness, you get a very perfect linear relationship. So there corresponds to one frequency for one thickness. So if you know the frequency the peak frequency corresponding to one particular material, you can predict the thickness of the material. This is one of the beautiful method by which you can absolutely measure the thickness of a material. It is very much applicable for your magnetic tubes, like what I have shown here. Next, please. This is what about sweep frequency eddy current technique. So I will sweep frequency. I am stopping. Yes, please. Minimum thickness is basically the skin depth frequency, whatever is possible to be detected. That is the thing. Even it is 0.1 mm also, it's okay. Okay. So, can we move on to the next topic? Any questions, please? So I have covered tube inspection, sweep frequency, and I will go to some flavor of artificial intelligence. I will give you. Actually, when you buy some instruments now, the vendor will give you a software. Okay, the software will do many things. Like for example, it will detect the defects automatically. You give a lot of data, it will detect in the data where the defect is there. Okay, I think I have seen in one of the shops in EDDY shops. They have used some software which will basically take data from hard disk, the stored inspection data, and will tell you wherever defect is present in the signals. Okay, so it is essentially automatically trying to detect certain features which are similar to defects, right? So how this can be achieved? That is used by using machine learning and artificial intelligence method. So we have some research work going on in this direction also. For example, okay, this is basically this is the framework on which all your machine learning algorithms will work in any conventional machine learning algorithms. It basically derives certain features from the eddy current signals or images, and then feeds to some learning algorithm. It can be neural network, it can be some kind of like cluster based methods, or it can be like some random forest statistical algorithms, and then it will give you some output, that is they are called labels. It may be either defect or no defect condition, which is a classification problem, or if you give an image and ask what is the size of the defect which has produced this image. So that is kind of a thing which is being explored in this machine learning algorithm. Okay. So for the major applications are automated defect detection from large amount of data, whichever data is having a defect signature. So that is what is the major application. Okay, ADR kind of situations where you in your radiography images and all you apply something called automated defect recognition algorithms. It is similar to that. Okay. So it will say that it will take a signal and it will go through the signal and then say there is a defect in this, there is a defect signal. Means I mean to say that there is an indication in this signal, okay, which could be defect, okay. So it can be either defects or image signals or images. I will show you one algorithm wherein we have used signals for automated detection, and that is one. And another one is sizing of defects. You give an image and it will tell you what is the length, width, depth of the defect, okay, which is not possible directly by eddy current method because the input-output relationship is not known generally. You get only a signal which says that whether defect is present or not. But what defect has caused this signal or image will not be known to anybody. Like you cannot simply invert it. Okay, it is not like an radiography or ultrasonic problem. Next, please. So essentially, what we are trying to do is like there is an input signal which is basically the eddy current X, Y components of the eddy current data. That is resistance and inductive reactance of the eddy current data. You can see there is a defect, which is the region of interest. We know it, right? How the machine will know it, okay? So you give it to a model, this data you give it to a model, the model will tell you wherever the impedance point is corresponding to a defect, it will say 1, okay? Wherever it is not defect, it will say 0, okay? We will see how it is done. Next, please. So essentially what we do normally is that from the eddy current data, we derive certain features. So we have taken the amplitude of the data in this case and looked at these 4 features which are very, very like reflecting the signature of the defect, okay, which are enhancing the signature of the defect. So which is given to a model. Click. We have developed something called a random forest model. Next, please. Next. So the model gives an output, something like this. You are able to see now. So wherever, up to that point, wherever the ROI is there 0 output is coming. Wherever defect is there 1 output is coming. So we can see wherever 1 is present in the output signal, we say that is the defect, okay. So this is the kind of automation that we are trying to do. And this algorithm is being extensively used now. Nearly 40,000 tubes we have analyzed from actual heat exchanger tube data. Okay. Next, please. Next. So to begin with, how this model can be trained. Okay. So we have to train the model with some known conditions. Okay. So for which we have taken some data from actual heat exchanger, analyzed something like 2,000 to 3,000 data. 60 tube data, we found 117 defects. So these were used as a training data set. Okay. So based on this data, we trained the model, and the trained model now will tell you wherever defect is present in the signal. Okay. Next, please. This paper is published recently in Journal of NDE, Springer. Next. So you can see the kind of robustness that the model has detected defects. Wherever defect is there, it has detected. It is the detected output that we are showing now. Maybe it is clear to you because you are seeing it as a defect, right? It is seeing as a signal, some indication. But how the computer says that it is a signal, that is where the crux is, okay? So it has very nicely detected, and we have evaluated the model with the independent data set. At the time of preparing this slide long back, 1,000 tubes were subjected to this data. Now around 40,000 tubes we have subjected to this data. And the model accuracy is almost 100% every time it detects. So what is of major concern is that there is a defect which the model should not say that there is no defect. Okay, there is a defect signal. The model should not say that it is no defect. So that is where we are much concerned. Okay, so that is called the false negative condition in the confusion matrix. So it has not told so far. It has told all the defect as defect. In addition to that, it has detected some false calls, but that is acceptable. So the model shows accuracy of 99.94. We are talking accuracy in terms of the data points, not as the whole signal as such. Okay, and 100% of classification of defects most of the times. And it is being used. It is like any other commercial software. It works. Okay, fine. Next. I wanted to talk about certain development that has taken place for sizing of defects. Basically what we are doing is, if such a defect is there, we are doing some measurement on the upper surface of the plate. We take an image of it. From the image we take certain features. For example, I have highlighted certain features up to F6, and same F6 features we can derive from another frequency data also, and some derived features also we have done. This was done by one of the research scholars who was working in our department. It was something like some 10 years before probably. And next please. And he used what is called multi-dimensional RBF neural networks. The advantage of this kind of architecture is that the interdependency of the defect features are taken intrinsically by this model, which may be very difficult to comprehend at the time now for you maybe, but it has certain advantages. That's what I wanted to say. Okay. Next please. And we have several classes for length, width, depth of the defects, and our accuracy at that time is 97, minimum 93% for quantification of defects. Okay. It will tell you, basically, you give an image, the algorithm will tell you what is the size of the defect. Okay. It's that interesting. Okay. So you don't have to know what is there going inside. Okay. So artificial intelligence is being used extensively in eddy current technique than any other technique which I know, because it is more apt for eddy current technique. I think I have covered quite enough some of the advancements like artificial intelligence, sweep frequency, RFIT, and some conventional tube inspection with advancements. I think with this I will close my talk. Thank you so much for your patient listening. So you can have interaction with me. You can mail me anytime. You can call me or for any doubts.
Any questions? So any questions? I think there are no questions.
There are no questions.
So very nice lecture, Dr. Arasu. You have one.
Yes, please.
Actually, you told about the AI and how you did automation in the eddy current testing. So I have one question regarding to that. AI is generally taking feedback and using that to help us. If I recall one lecture which was provided by ISNT, in radiography they do not have enough data for slag inclusion because it is always unique in orientation or in everything. So is there any possibility that in eddy current testing there is some unique indication that is not detected before, so it just accepted it and just go on to the next thing?
No, defect indications are very rare occurrences. Actually, you have to look at archery detected defects. Like for example, I told now 60 tubes we found 113 indication. That is obtained from detected tube, which is something like some 40 years old. The inspection was done. So like this, if you have some age component in which defects are bound to occur, you can have the data. But if you don't have data, you can generate data by using model-based AI models also is possible. You can generate it through model. So for example, like you do a finite element model of the weld defect and generate a variety of images for a slab distribution. There are so many softwares available, like Siva software, for example.
Okay.
Siva you must be knowing, right? There is an entity software called Siva software, which is used for radiography and eddy current and so it's possible. It's possible to generate such images.
Okay.
But it will not be like practical images. So that is the only.
Thank you.
So any other question? Anybody? Fine. So thank you very much, Dr. Arasu.
Thanks a lot.
It was very nice that you interacted with people, and
Yes.
they are very happy. It seems.
Yes.
Thank you very much. Yes. We will have a group photo first and then we'll disperse for tea break. We'll have a group photo first because they want to leave, and after that there will be practical demonstrations. Okay, so after tea you have to come back here again.
Hello. So we'll start practical sessions right now. So on your screen, you will be able to see those practical sessions, and these practical sessions are conducted by Mr. Chandrakant sir, who is representing 4-Star Instruments Private Limited, which is sister concern of EECI Mumbai. Okay. So I will hand over him so that he will show you the demonstration so that we could jointly see the demonstration on the screen itself. Thank you, sir. Thank you.
Good evening, everyone. So you have learned the theory of the eddy current. Now we will demonstrate how this eddy current actually work in applications. One of the task is we have a sorter machine, eddy current sorter machine. The other machine is eddy current crack detection, and third one is eddy current conductivity meter. So we'll start with sorting machine. So here you can see a screen of my software. There are different equipment, like this one is TCL, Magnetics TCL, which is a sorting equipment from Foster, Germany. Then this is the coil which is connected to the instrument, and a software is running inside the laptop. So this is a portable you can say, you can automate also this instrument, this kind of equipment. So I have already done the calibration. Now I can show a demonstration of the same. Like we have done the sorting of this fasteners. One of the fastener is like a hardened one to 45 HRC, and the other is soft one. So I'll show you how this can be sorted. So we are in test mode. There are 3 modes. One is system, where you can do the automation. There is setup mode. In that you can do the calibration. Like you can see the calibration setup here. Then test mode, you can test it out. So the part which is inside is now in the coil. I'll get it tested. I can press a trigger. So I'm triggering it. I'll get a OK reading because this is a hardened one. I've teach this part as a OK part. And likewise you can trigger other part also. You can get a similar reading. And if you put the softer one, you'll get the different reading. This kind of. This is actually a eddy current sorting application, which is normally used in automotive parts. Manufacturers, they use this machine to get sort on the basis of hardness, case depth, microstructure, so that the machine or the automotive don't get failed later. Because of case depth, hardness, the material should be strong enough. So this is a prior to assemble testing procedure. So this one is the TCL. If you have questions about it, I can answer the same. Microstructure as well. So it can sort comprehensively, like it will not give you a result of microstructure, hardness or this case depth. It will give you a comprehensive result. If anything is different, it will sort your product accordingly. And next machine is portable crack detection machine we have. So this machine is normally used in application of like aerospace as well as some application wherein the cracks are not like acceptable. So what we do is portably do test the cracks. We calibrate the machine according to the crack parameters, like whatever cracks which are permissible, we do teach the machine, and accordingly, if you have the cracks bigger than your calibration, this thing, acceptable range, then you'll get it sorted. Like he will show you the thing. Okay. Yes, this is. So wherever it is cracked, it will show you a pink, and you can with a portable machine.
What is the accuracy of the system? Because this crack is visible also.
Yes.
Visually we can also detect.
Oh.
In my PPT, what they have done, that you need a difference.
If your stress to noise ratio is 3:1, then crack is detectable. So So if your stress to noise ratio is 3:1, you can catch the crack. Main is stress to noise ratio. And probably our instrument have an accuracy of like we can detect a crack of 30 microns minimum if the machine is finished. If it is forged, then probably 80 to 100 microns we can catch.
Visual inspection, we can also examine 100 or 50 micron defect also we can see.
Visually you can see, but that is man dependent. It's not a man dependent machine. You can easily this thing. And also it is also man dependent. That's why the errors can occur. In this you can see a better this thing. Crack detection. Portable crack detection. Detection. We have a automation also. Like if you can see my standee there, in that I have shown two different equipment, like magnetized TCL is one of the 8 and other is statograph CM. Statograph CM is a equipment which can be automated. Like if you want to sort on basis of cracks automatically, that also possible. You can do it. So that is the answer for your question, why it is better than the MPA. Yes, to certain extent it is possible.
Yes. We should have the same specimen as a standard.
Yes.
So with this we cannot test. So this is
We have different probes for that application, like welded, or you can test the thickness also. That also can be done. So we have different probes for that.
This machine is for only crack detection. Okay.
Yes, crack plus you can say thickness also you can measure, tube thicknesses.
You can do demonstration.
Yes, demonstration.
These are
Wait.
all the parameters. We can select the parameters from here. Yes, you can. You can select the parameters. You can select all the parameters from here. In this, you can use right now for this probe. I have already selected all the parameters like frequency, zero offset, gain, phase, bridge resistance chart, trace time threshold. What I will do here, I will start the calibration of the machine from auto set. This is the probe. The uh, the machine detect our probe. So, so our software automatically detect the probes when you connect the probe to the machine, and then we go to next. Test this probe on the specimen.
These are primary calibration procedure, like he is teaching machine the cracks. Yes, wall thickness also can be measured. Yes. Like if you have, yes, if your wall thickness has reduced, that can be detected. Like if you teach the machine that this wall thickness is acceptable, like pipes and all, and if it has been reduced with the this thing, then it can detect. But with different probe, we cannot demonstrate right now. We have a probe for crack detection. We'll be showing that. Okay. That I need to check actually. But we usually follow the procedure wherein we have a policy, we do ask samples, we validate that, and accordingly we submit the further proposals. Okay. Now the third machine is conductivity meter. Like if the area is shown about. Conductivity meter. Yes. The name of the equipment is Sigma test. It's not sorting, but you can detect a value. In eddy current sorter, you will only get a this thing. You will not get a value. It's a comparator machine, so you will only sort on basis like okay and not okay category. Here you can detect some values like conductivity values. This is also a portable machine. Yes, conductivity. Value it will give. So you can see the standard in that percentage ISES, this thing is there for copper and silver, and accordingly is checking. So he'll show you the from backside also how it give the conductivity.
We have already calibrated the machine in our job. I will start with the testing. I will start with the copper.
So he's starting with copper. So it has already written a value. He'll show you the value, what it is getting exactly.
And if we change the frequency, still the value will be the same.
Yes.
Here I have changed to 120 kilowatts, then 240 kilowatts. Now in 240 kilowatts, I am trying to see. And second one I have silver. Silver I have 4.28. In this I will get 4.26. 6 to 8. And in this we have used manual, touch and continuous. It's like
Even we have a continuous thing in this, like he'll continuously touch the part and will show the value changing to the different this thing for copper and silver.
Now I will go directly from copper to silver in continuous mode. The value will change.
You can see the values are changing.
And also this can record all the like this phone, the report, you can record the data if it's changed. And after that there is a USB and memory cards you can insert and you can export.
Even you can automate this equipment. It has a Ethernet cable. You can automate it and get it this thing. Industry for this equipment is mainly we supply this equipment to copper manufacturer and some steel manufacturer. They also prefer this.
And also the calibration process is also easy. There is a video on YouTube for all the machines. You can go through with that calibration and you will see it's very simple with the first machine.
Yes.
Okay, we can do the geometry of crack for example. How to check the cracks?
Cracks.
And the actual object.
No, we don't have a crack object. We have only the calibration this thing. I don't have a crack object. I do have a sorting samples that I have shown you. Crack also he has shown that standard is having cracks. So he has shown that the cracks are like, if you want to visualize, you can visualize this by coming here.
For any machine available for demonstration right now?
Which machine? Yes, we have multiple machines available for demonstration. Like, which machine you are simply asking? Crack testing. In Pune you want to see. This is eddy current sorter, sir. This is eddy current sorter. Yes. Yes, but one is sorting machine. On basis of hardness, sketch depth and microstructure it can sort. Second one is crack testing, portable crack testing machine. It will not sort your part on basis of this thing, but it will, a probe based machine That is a coil-based machine, and this one is conductivity meter machine. Any questions? Those who want to see this machine can come here and we can demonstrate it. Yes. Okay, right.
So thank you very much, Chandrakant, for coming here all the way from Mumbai and giving us a very nice demonstration. Thank you very much from ISNT Pune chapter. So as a token of appreciation, we would like to share this memento. काही बघायचं असेल तर बघू शकता. इफ यू वॉन्ट टू सी
Hello everyone. Today we are introducing EDDY Make ISNT machine for specially designed for tubular inspection in eddy current testing. So currently we start the magnify software of EDDY Make, and this is ISNT machine. We connect the probe. This is bobbin probe. This is bobbin probe, and this is the reference standard for calibration purpose. So first step is to create folder, project folder, give the path and give the name as per your required. And select the folder. After that, create setup. In this setup, select geometry as tube from ID, because currently we are doing from bobbin probe. Otherwise, if surface, we can select surface also if we have surface probe. Then application generic and select material. This material is SS304. So we select material. After selection of material, resistivity, permeability and velocity, software automatically selected. After that, select wall thickness. Currently wall thickness is 1.8 mm. Select outer diameter. Outer diameter is 19.05. And select length as per your job. If heat exchanger tubes are available 6 meters, then input length 600 mm. And select next. Select here technique, ECT, from model, standard bobbin, and select probe. Next. Here is the scan definition. Scan position from acquisition rate, typically probe speed, acquisition sizing. When we do manual, in this setup we didn't change anything. So here is data definition. Here is to select differential channel and absolute channel. Data definition. Here is the select adjust your gain. After we scan the tube, standard tube, then after we change the gain from data definition. Second one is here frequency, like F1, F2, F3, F4. There are 4 frequencies are here. So if we click suggest, automatically and S, automatically select the frequency. After scanning, I told you to select how frequency is correct or not to check. Then next, here data definition, we can add mixed channel also. Select in mixed channel which channel you want to mix, like differential F1 and differential F2. It's depend from your side. Then next, in data processing, here is the filter selection, like low pass filter and medium high pass filter. So we now select low pass filter because we didn't select medium high pass filter, because selecting of medium high pass filter, it alters the defect signal. That's why we not select. In worst condition, then we select. Here is the detect landmark, like it automatically detect when start and end for given length, like tube sheet insert and tube sheet out. So we give length 0, tube sheet insert 0 and tube sheet 0 out. Then next, here is the calibration points, like which types of you have artificially defect in your reference standard. Now currently we have 50% OD, 20% OD, through hole, 80% flat bottom hole, 60, 40, 20 flat bottom hole, and 20% ID from inside. So we check that defects are here or not. If not, we can add from list. So hole 80, 60, 40, 20 available. Here is the ID 10%. So we change that 20%. And change in size also. And OD 20% is available, 50% we select. Here is the calibration point, measurement method, references, voltage. We can change it from here as per difference code and customer requirement. There is a sizing curve selection for different channel. Like here I select absolute F1, F2, differential F1, differential F2 and mix. Okay. Currently support plate is not available, so I remove the mix channel. Then next, here is this sizing curve configuration. This is configuration for absolute F1's method. Absolute channel is for large defects. So in absolute channels, we take groove type defects, and differential channel we take pitting type like flat bottom hole and through hole. Okay. So in measurement method for absolute MP is correct. Shape is best fit linear, and select the grooves. So best fit linear required only 2 defects to create sizing curve. So next is for absolute F2. So same process here, because absolute channel is here. Then next. So now here is configuration for differential F1 sizing. So as I told, differential channel is for pitting type defect. So we select whole, flat bottom 80, 60, 40, 20 and ID group 20. Then next, sizing curve for differential F2 same as a differential F1. Here is the indications code mentioned. You can add or delete also. So we keep standard indications code like COR means corrosion, CRK means crack, DNT means dent. You can change as per your requirement. This is the display configuration. We keep it as it. Then next, this is the selection of how much strip chart required. And select the which one you want. I selected 2 strip charts and 4 residues means impedance plane. Okay. Now currently setup is generated. I started. So this is the display before calibration. So we set the channels, select the channels like differential F2 and absolute F2 and differential F2 I select. You can change as you seen which you want to. So I select in strip chart absolute F2 and differential F2 because this is the main frequency. F2 is the main frequency. That's why I select absolute F2 and differential F2. You can change usages as per your requirement. Absolute F1, I take absolute F1 and absolute F2. Second one is differential F1 and differential F2. Okay. Make sure this strip chart arrow is upside. Okay. After that, machine is already connected before the starting stop software. Now currently we balancing the standard. We select the area where defect is not artificial defect, where that good area we selected, like here we take measurement from this end. Select कर ऊपर से डालना. We select the good area like this and then insert in the tube. Okay. Then we null means like balancing. So now we give the software this is the good area means 100% defect free area. Now we scan the whole tube. Scan. Stop. So we check the which signal is whole signal. Like I select this is ID20 whole 20, 40, 60, 80 and 100. We select the whole because in eddy current whole is the standard reference. We set a whole signal at 1 volt and 40-degree phase angle. That's why we calibrate first whole. select the hole, go to calibration, first system calibration, channels calibration, select hole and download. After that calibrate. So now you've seen all signals are improved. So first after that selecting the hole, check the all channels like this. Differential F2 is 1 volt 40 degree, 1 volt 40 degree, but absolute channel 1.85 because of not proper selected hole. So I zoom it and tightly selected. And repeat the again. Okay. After the whole calibration, we go to sizing curve and calibrate remaining all defects. Like this is hole 80, 40, 60, 80. Sorry, 100, 80, 60, 40, 20 and ID hole. So select 20. This is 20, flat bottom 20. So we calibrate. After that 40 is calibrate. 60, 80, again 100. After that ID 20. Then OD 20. This defect is 20. After that this is 50. Currently calibration is again because calibration is not done yet correctly, that's why this message is come. So I redo the calibration. Currently absolute channel, which channel we are not calibrated, not shown because software key is not available currently. So this is the calibration process. After that we create list like how many tubes are you want to do, like heat exchanger, each row have 10 tubes and 10 rows. So we enter number of rows in component like 10, starting number of rows and starting interval 1. Enter. So enter each like number of tubes each row like 2, 3, 5, 6, again 6, 5. Then create. After the starting, the list is generated automatically, and after that we remove the setup mode. After removing setup mode, we can acquire each tubes. Like acquire. Automatically message come to save setup. So we save setup. Rename it and enter OK. So setup is saved. Now we collect the data, and after collecting the data we can interpret and generate report. Like acquire 2, 3 tubes. When we acquiring, automatically come to next tube which as a sequence. So we scan also as a sequence as we created list. Okay. Any questions? Yes. Date and no, automatically it saves file. Its file have saved like you save JPG file, PNG file. Graph? No, no. Possibility of? No, no. Not manipulation. Only you can delete data. That's it. If you scan in one tube 2, 3 times, then it can manipulate. Yes, yes. It can be. Yes, yes. Yes, yes. Yes, sir. The standard block take which tubes you have same thickness, same OD and same material. Yes. Each time you have to create this standard block. Anyone? Okay.
So, thank you very much for giving a very good demonstrations of tube inspection. And as a token of love, please accept this. Yeah. So thank you very much for attending this particular session for today. Oh. Eddy current testing and its applications. So see you tomorrow for infrared testing and applications. Thank you very much for it.